So good morning, everybody. This is the fifth and last day of the spring school. And today we have Liang Jiang from University of Chicago, who is going to talk about measurement and control for quantum error correction. So Liang Jiang is, has worked a lot on, his work research basically focuses on using quantum control and quantum error correction to protect quantum information. And he's worked on a broad range of topics with this, including quantum sensing, quantum transduction, communication, and computation. So he will, this is the outline of his talk here, and he will now start. So Liang, thanks very much and for doing this. And also I should say that if you have any questions, please either put them into the Q&A or into the chat. And Chao Xuan and Chan here are moderating, and they'll pass those questions on. And if there's anything really urgent, we'll have those questions live. Otherwise, they will answer them in the chat and Q&A. So Liang, over to you.
Yeah, well, thank you, Bajita, for the nice introduction. And also I'd like to thank also Chao and Chen, who are also helping with the answering and moderating the lecture. So today I'm going to talk about like measurement and control for quantum error correction. And so the plan would be like I'll briefly introduce the quantum error correction, listing the quantum error correction criteria, and introduce the stabilizer error correcting codes for qubit systems, and then talk about the bosonic codes for bosonic systems. And if there's time, I'll talk a bit about the fault tolerance and threshold theorem before we get to kind of like various control approaches for quantum error correction. So I think that since like there is a, okay, it will be helpful like if people have like questions and so on, just type in, and I think Chao and Chen can help like let me know in case there are questions that I should address during the lecture. So the plan is actually, let's first start with the introduction of quantum error correction. So I think that right now, I think we are getting into the noisy intermediate scale quantum era, and there are already quantum advantages has been demonstrated. And so now the next question is actually, can we get the full power of quantum technology? And so in practice, there are like major challenges that there are various practical imperfections and noise. Okay, some of those kind of like imperfection noise can be improved at the physical layer by like having a better design or like a more robust control. If the errors are actually like at the unitary error, then maybe you can use the dynamical decoupling schemes to suppress them. And sometimes that those errors may not necessarily be like just the unitary errors. They may introduce entropy to the system. For example, there may be like a random bit flips or maybe like a healing of the system. And those errors actually introduce entropy to the system. And then just the unitary control will not be able to extract the entropy from the system. So what you need to do is actually to do like active quantum error correction that take away the entropy from the system to cool the system down. And this is in some sense might remind you of cooling. However, the task of quantum error correction is actually more challenging than cooling, is because while you want to take the entropy from the system, you also do not want to destroy the encoded information. Okay, so basically you need to kind of take away the noise, but not destroy the encoded information. And so that's actually a kind of a major challenge for quantum error correction. And so now actually let's kind of like think about what kind of noise we may have. So generally, maybe your system store quantum information, the quantum memory may have errors. Moreover, when you want to use quantum gates to correct those errors, the operation may introduce additional errors. So this actually makes things potentially more complicated, because while you're doing error correction, you might introduce more errors. Okay, so that's actually naturally leads to the threshold theorem. So basically your error from the operation should be low enough before you can actually like do error correction to take away noise without destroying the information. And for simplicity, let's first focusing on just the memory error. Assume that our qubits may suffer from decoherence. Okay, and later on, I will talk about like how to do the operation more fault tolerantly, but that probably will be the later part of this lecture. So before we talk about like a quantum error correction, it probably will be convenient, also maybe like a warm-up, to start thinking about classical error correction. Okay, so suppose we want to send a bit over a noisy channel, which will randomly flip the classical bits. So there is a probability PE of a bit flip error, which will convert 0 to 1 or convert from 1 to 0 from the sender to receiver. So this is kind of like a binary, kind of a bit flip error channel. And the way to overcome this random bit flip error is actually to introduce redundancy for our classical coding, which actually the idea of redundancy actually holds more generally also for quantum coding as well. And for example, we can use 3 physical bits to encode 1 logical bit. So the logical 0 will be 0, 0, 0, and the logical 1 will be 1, 1, 1. Okay. Now consider, suppose we start from logical 0. There is actually going through this noisy channel. So there is a probability P for each bit to undergo a bit flip error. So there's a chance that, okay, none of these bits get flipped, and that occurs with a probability of 1 minus p to the cube, because it requires all of the bits to have no bit flip, which each has a probability 1 minus p, so you need 3 bits to have no bit flip, so it's to the power 3. And the probability, for the case with a 1 bit flip, there are actually 3 possible situations where the bit flip could occur. And for each case, there's a probability of PE for the bit flip and 1 minus PE square for the other 2 qubits, other 2 bits which do not have a bit flip. So this is the probability for the 1 bit flip error. And similarly, you can compute the probability for 2 bit flip error and the 3 bit flip errors. And if you add all these probability up, it should be equal to 1. Okay, so now actually with the repetition code, we actually can correct up to 1 bit flip error by the following procedure. Basically, we measure all 3 classical bits and check if they are same or different. If all 3 classical bits are the same, we basically do nothing, because very likely there is no bit flip error happen. And if they are different, then indicating definitely some bit flip error happened. And then we do actually the majority voting by picking, say like, okay, depending on whether the majority is 0 or 1, we actually follow the majority. For example, in the case of 0, 0, 1, we will say it will be 0, 0, 0 as the original state, because it's more likely to have a bit flip on the last bit rather than having a bit flip for the first 2 bits. Therefore, we actually assign and follow the majority voting rule. And in this case, basically, we will be able to correct no bit flip or single bit flip situations. While if there are 2 bit flip or 3 bit flip, in those cases, we will not be able to correct those errors. And so therefore, we can add up the correct situation, which is the case with no bit flip error and the case with 1 bit flip error. We can add them up. That gives us the probability of getting the correct answer. And you can add those up, and here is the expression. Basically, it will be mostly actually suppressing the error PE, which usually is a small number, to the 2nd order. As you see from the expansion, that the linear order of PE will be suppressed. And you only get the quadratic and the qubit term. So when PE is very small, this number approaches 1. And when PE, and also the effect of the PE is suppressed to the quadratic. So therefore, this nonlinear term, actually like a leading nonlinear term, indicating that you have suppressed the small bit flip error to the 2nd order. And you can actually plot this function. Let me just maybe manually just do it here, where the horizontal axis is PE, the vertical axis is the P correct. And you'll find that actually this particular function it has 3 fixed points, which are associated when PE is 0, then P, sorry, let me just draw it as a 1 minus PE for convenience. So when 1 minus PE is 1, that indicating PE is 0, your P correct is actually equal to 1. When 1 minus PE is 1/2, PE is 1/2, P correct is 1/2. And when 1 minus PE is 0, that means PE is 1, you will find that this is also equal to 0. So that indicating there is kind of like a fixed point of those 3 fixed points. And you can show the entire function here and compare to the dotted line, indicating that if initially your PE is very small, that's down here, 1 minus PE is very close to 1, you actually can push the error to something even closer to 1, okay, at the logical level. So that indicating the P correct will be larger than 1 minus PE if 1 minus PE is larger than 1/2. And that's actually the fixed point in the middle. So therefore, we actually can get an improvement in this region where we actually have a small error, and using repetition code and majority voting, we can improve the P correct and suppress the error to the second order. And so why it's actually important to suppress the error to second order? Because in principle, if we can suppress the error to second order and we can do error correction frequently enough, then we can actually make the error arbitrarily small. So here is kind of the idea. So suppose we want to protect the information for total time t. Okay, and suppose there is an error rate gamma for each bit flip to occur. And so during small time tau, the bit flip error will be p tau, which is gamma times tau. Okay, so now if we divide the total time t into n small sections, then each section will have a time tau, which is t over capital N. And let's assume that capital M is large enough, then basically the error for the total probability of having no error for entire time t, assuming we do the repetition code, then that will be the value of 1 minus 3 gamma t over n to the power 2. So here, basically we are identifying the gamma tau, or p tau, to be equal to PE. By this identification, we can plug into the expression. And because n is large and the p tau or PE is small, so we can ignore the third order term and only keep the second order term. So in this way, we basically use this expression of p correct and plug in here. And since we divide the entire evolution into n sections, then we need each section to be correctly correcting the error, and then repeat n times, that's why to the power n. And you may notice that this gives you kind of a series expand. You can actually expand it in series because assume capital N is large. The leading contribution will be actually like 1 minus 3 gamma t square over n square times n. So notice that the leading correction due to the error actually decreases as n goes large. Therefore, basically, when n is much larger than gamma t inverse square, you will actually have a good suppression of error so that the probability after the entire storage and after time t will approach 1. So this is actually kind of the idea of why we want to suppress the error to second order, because in principle, with this, we can actually have a quadratic suppression of the error, while the accumulation of n steps only scale linearly with n. So therefore, overall, we get a suppression of the error after the entire duration. And this idea actually can also carry over to the quantum domain. So now, what's the difference? So far, we only talk about the classical bits. However, when we go to the quantum, there is an important procedure that we actually cannot do. Because classically, we're saying that we want to measure all 3 qubits or all 3 bits. However, if you want to do it as a quantum information, then we actually cannot measure our quantum bits because that would collapse our quantum states. All right, so now we actually need to think about a different procedure that to get around this limitation and try to reproduce kind of what we have like achieved in the classical coding. All right, so if they assume that's clear, and let's move on to the quantum case. So now let's get into the quantum error correction. So the major challenge is actually twofold. So I mentioned the challenge that we actually cannot measure individual quantum bits because that will destroy the information. And the second thing is actually more like a conceptual, which is actually in the quantum case, we know that the errors may not necessarily just flip in the bit. It may undergo a unitary evolution, which may continuously rotating your bits or continuously inducing defacing error. So therefore, for such a continuous error, it's actually important to think about, okay, can we really handle such a continuous error? Because it's kind of like evolution could be a superposition of error or no error, and would that cause a trouble when we try to correcting them? Okay, so that's actually leads us to actually give maybe we should think about more general model about what the quantum error will look like. So first of all, let's just restrict ourselves to the quantum bits, qubits. And for the qubits, I think that maybe in the first few lectures, people already talk about we have a bit flip, which you can represent it as a poly X matrix with off diagonals being 1 and diagonal being 0, or have a defacing error, which is a poly Z matrix with diagonal being 1 and -1 and off diagonal being 0. And you can also combine the bit flip and defacing together. Then you can basically multiply the bit flip and defacing poly matrices. And to make it Hermitian, add an extra I, so that corresponds to the poly Y matrix. So these are the 3 Hermitian matrices together with the identity that can span all the Hermitian matrix you can write down. Okay, which in principle you can span any Hamiltonian evolution using these poly matrices. Now, let's consider an arbitrary unitary evolution over a qubit that may couple to the environment. So this is kind of general way of thinking how the open system will evolve. So with such a unitary evolution, then what happened is that you can always expand such an evolution in terms of superposition of 4 terms, which the first term corresponds to there is effectively identity acting on the system. The second term corresponds to the bit flip on the system, while environment goes to some other states. The third corresponds to there is a combined bit flip and defacing, and the last term corresponds to there is just a defacing on the system. And notice that these extra states for the environment in this general notation may not necessarily be normalized, but it's okay because all we care is actually what happened to the system. And notice that for this general evolution, the system, they actually may evolve into some if we take into account the environment, may evolve into some superpositions of X and Y and Z evolutions. And also these environment states may not necessarily be orthogonal. But that's okay, let's just take that, and later on we will see that those superposition or continuous errors is actually can be taken care of by error correction. So now this is for the simple model for single qubits. Now let's consider for n qubits, and you can generalize that instead of writing down the poly matrices for single qubit, you can write down the general poly matrices for n qubits. So generally, if you have n qubits, each qubit may have 1 out of 4 choices. So the n qubits altogether, you have 4 to the n choices for the errors. Okay, so now it's actually a good time to make an important claim, a disclaim about okay, what we really want to achieve for quantum error correction. So first of all, we're not trying to correct all possible errors because it's impossible if you want to do logical operations, but your error will correct. So it's impossible for error correction to correct all errors, including logical operations. Okay, if that's the case, then there's no way you will be able to do logical operation because that will be identified as an error to be corrected, or there is no way to encode the information if you can correct all possible errors. So the goal is actually to correct the common sets of error that's important in practice, so that we will be suppressing those dominant errors to high order, and so that effectively in the logical level, we'll have much efficiently suppressed error. And this is actually important because our goal is not to correct all the 4 to the n possible poly errors, but our goal is actually to suppress a subset of those errors so that we will be able to kind of suppress the error to high order and proceed with our computation. Okay, so with that stated, so now the error correction task is actually to identify a subset of error. And here it's just a subset of all possible poly errors so that we can use some like a collective measurement, as we'll talk a little bit, to diagonalize which error in the subset so that we can correct. Okay, so now the task is actually, for example, we might be able to project these different errors in that subset we want to correct into different subspaces. And therefore, by identifying those different subspaces, then we can perform some unitary operation to undo those errors and map it back. And here we're actually like using one of the properties for the poly matrices is that the poly matrix, on one hand, it's Hermitian, on the other hand, it's also unitary. So if we identify certain poly errors, in principle, we can apply that unitary inverse to undo the error. And so that's why actually in this case, if we identify, say, the first qubit has a bit flip, actually the procedure to correct that error is actually to apply, again, undo the bit flip by flipping it again. So that allows you to recover the information. Okay, so here I'm talking about kind of like maybe at the higher level, like how to do quantum error correction for the qubit case. So now let's actually look into some like specific examples. So the example will be actually the 3-qubit code again, but this time it's a quantum bit, not a classical bit. So to specify what the code is, it's actually, we can just define what's a code word. Or more generally, we can just say what is the subspace that's used for quantum error correction. So in this case, we're actually having the logical 0 being 0, 0, 0 for 3 qubits, and logical 1 being 1, 1, 1 for the 3 qubits. And any logical states, or any pure logical states, can be written as a superposition of logical 0 and logical 1. Okay, again, very similar to our classical code case. So if there is no error, then we actually, so here we're considering the bit flip error. Okay, if there's no bit flip error, then we still maintain our state in the logical space as the original input. And let's assume there's a probability PE for the bit flip error. Okay, tentatively assume that it's kind of a process that with a fixed probability for each qubit to have a bit flip. Then the bit flip error will, or no bit flip error for 3 qubits will have a probability of 1 minus PE to the power q. And the probability to have a 1 bit flip error out of one of the 3 qubits, it will again be the same as 3 PE 1 minus PE squared. And similarly, we can do the 2 qubit flip or 3 qubit flip. And now the goal is actually to correct errors all the way up to like a single qubit flip. So the defined set of error operators we want to correct is actually consists of identity, bit flip on the first qubit, bit flip on the second qubit, or bit flip on the third qubit. And notice again, this is a subset of all possible bit flips that you may have, because that would give you actually an extra 4 more terms, including simultaneous bit flip on qubit 1 and 2, 2 and 3, 3 and 1, or simultaneous qubit flip for all 3 qubits. So those are possible errors, but our goal is not to correct them. Our goal is actually only to correct the bit flip associated with individual qubit flip. Okay, so that's actually like the task we want to achieve is saying like, if any of those 4 events happen, we will be able to restore the encoded information. So now, before we talk about the procedure of how to do it, let's maybe think about the feasibility of like, okay, what is actually like, whether or not we can do it. So with this particular coding, so we will actually first define something called the logical space, which is the Hilbert space spanned by the logical 0, logical 1. And the logical space, which we call it the P0, is the space which is spanned by logical 0, logical 1, which corresponds to all 0 and all 1, or their superposition or mixtures. And then if there is a bit flip error occurred to the first qubit, then it will go to map to a logical space, which is spanned by 1, 0, 0, or and 0, 1, 1. And that gives another 2-dimensional space. And notice that the space, which you call the P1 associated with the first qubit has a bit flip, is actually orthogonal to the P0 because the basis spanning the P1 has no overlap with the basis states spanning P0. Similarly, if there is a bit flip on the second qubit, then we actually go to the error space associated with that we call the P2, which is spanned by 0, 1, 0 and 0 and 1, 0, 1, which is associated with having a second qubit at a flip. And finally, if the third qubit has a flip, it actually maps the system to another 2-dimensional subspace, which is spanned by 0, 0, 1 and 1, 1, 0. And notice that these 4 subspaces each has dimension 2, and they are all orthogonal to each other. So therefore, that implies that actually, first of all, it's a good news that all these errors, in principle, there exists an operator to differentiate them. Okay, and moreover, we may find that actually like in principle, if we start for any superposition, you start from logical 0, logical 1, it will, if there's the first qubit that has a bit flip, it will remain to be the same superposition with the same coefficient, except the basis states goes from logical 0 to the x1 logical 0, and the logical 1 goes to x1 logical 1. But the coefficient still remains the same. So that's actually important because if there's anything kind of happen from P0 that bit flip had a bit flip error on the first qubit, it mapped to the P1. But the superposition still maintains, so in principle, you can design a unitary to map it back from P1 to P0. So that indicates that we're not only able to detect and differentiate what error happened, moreover, we can also restore it to the original logical space and maintaining the initial superposition. Okay, so now let's actually look into more detail. So first of all, we can define these 4 subspaces, and for each of them, we can define a projection operator. So the P0 is just the projection, which is defined to be the sum of the projection to its basis states. So since the basis states is logical 0 and logical 1, each of them will have a projection, and we just add them up. And that defines the projection to this 2-dimensional subspace associated with the logical space P0. And similarly, you can define the projection to logical space P1. And notice that in principle, we can write it as x1, a projection associated with the state x1, 0 logical, which effectively is sandwiching the projection to the logical 0, sandwiching it with the bit flip x1. And similarly, for the projection to the other one is a projection to logical 1, sandwich that operator with x1. So effectively, the P1 operator can be written as sandwiching the P0 projection with x1. Similarly, the P2 projection is essentially like a sandwiching this projection on 0, logical 0 operator, projecting to a logical space with the x2 polys. So this gives you the definition of the projection to all these 4 different logical, these different subspaces. And you can verify that all these projection operators, they are orthogonal to each other. Now, some basic property is the definition of the projection to the logical space should preserve the logical state. So when it's acting on the logical state psi logical, it should give you psi logical. However, if you're applying a projection to some other space which is associated with the error space, then we know that the logical states should have no overlap with those subspaces. Therefore, when you apply a projection to the error space, associated with the error space to the logical operator, it will be 0. However, if you apply an error to your logical states, that actually map you to the J's logical subspace, some states in there. And then if you apply the projection to the I's logical space, then this term will vanish unless I and J are equal. So if that's the case, if I and J are equal, then you actually still preserve the original states, or otherwise it will be 0. So basically the projection really gives you a way to pick up that particular space, pick up any component in that particular space. And moreover, if you have some superposition of error, say like, okay, if there's a superposition of error or no error in the P0 and P1 space, and when you apply a projection to the P1 space, you will either get two possibilities. Either that states kind of being projected to the P1 space with a finite outcome, or with actually getting to that space, or it's actually being kind of like not projected to that space. So you kind of like that collapses the system into either in the error 1 space or not in the error 1 space. So that actually like destroys any initial superposition that you may have. And then you get actually a probabilistic outcome that whether or not your state is in the space that you want to project it out. So that's actually important because that removes this ambiguity of having a superposition of errors, because in the end, what happened is you just identify whether or not there is error without any ambiguity about the superposition. All right, so now assume we can perform these projection operators as we'll discuss in a minute. Then what happened is that once we did the projection, it will pick up the component which is associated with that projected subspace. And because these projections are orthogonal to each other, then there is no ambiguity whether or not, okay, like which type of error happened. So then that achieves the task. Actually, we will be unambiguously identify no error, bit flip error on the first qubit, bit flip error on the second qubit, or bit flip error on the third qubit. And then we can actually push it back and perform a unitary operation correspondingly to restore it back to the original logical space. Okay, so therefore, the whole scheme, by performing the projection to different subspace and then perform the following procedure. If it's in the logical space, you do nothing. If it's in the I's subspace for I equal to 1, 2, 3, then you flip the corresponding qubit to correct the bit flip error. So now just remind ourselves that this corresponds to the case with no error and the single qubit flip error. Okay, so basically we can add up these error probabilities, and that corresponds to the total success probability of correcting no error and the single qubit flip errors. So we can add them up as what we did with the single qubit case. And what we see is that after the correction, the success probability of correcting the error is equal to 1 minus 3 times PE squared plus 2 times PEQ. And again, there is no linear term, and you actually successfully suppress the bit flip error to the second order. And we can show that this P correct is larger than 1 minus PE when PE is less than 1/2. The same math as we show for the single bit flip error. Okay, so then we can extend what we have kind of like discussed for the single qubit case, for the single bit case, is that this will actually allow us to, since it suppresses the error to second order, then we will naturally be able to have a long storage if we can repeat such a quantum error correction frequently enough. Okay, and now, moreover, if we have some errors, as I mentioned earlier, could be a coherent superposition of no error combined with like a bit flip error on the first qubit, then actually the projection will destroy such a superposition. So therefore, in the end, you'll get two possible outcomes. It will be either in the logical space or in the one error space. And if it's in the logical space, recover the states. If it's in one error space, it's indicating you should unflip the first qubit to restore the information. And this converts from a quantum superposition to a classical mixture because of the projection. And that destroys the coherence and avoid the ambiguity of a continuous, like a quantum superposition error. And therefore, it actually can correct any superposition of no error or one error, or any superposition of the errors associated with the span of those error operators. So then the question would be actually, how do we kind of like, okay, so now the detailed procedure is actually we want to implement such a projection with PI. All right, so the key idea is actually the following. Instead of measuring individual qubits, which will collapse the state, we actually should perform some collective measurement, and without disclosing what the state is. Because if you're measuring individual qubits in the Z basis, if it's 0, it will indicate the encoded state is logical 0. If it's 1, it will indicate the encoded state is logical 1. However, if we measure collectively as Z1 times Z2, then the product Z1, Z2 should always be equal to 1 if there is no error, because the original code word is 0, 0, 0 or 1, 1, 1. And the Z1, Z2, when you multiply them, and kind of it will always give you +1. Okay, so that will give you actually like some verification that whether or not it's in the logical space without disclosing which particular logical state it's in. And so basically we can measure Z1 times Z2 and Z2 times Z3. And those are Hermitian operators we can actually perform measurement. And since these are product of Pauli matrices, they should have eigenvalue +1 or -1. Okay, and these, as later we'll talk about, they correspond to stabilizers that we can extract the syndrome. So now we can actually, since each of which can have value + or -1, we're measuring two such operators. There are 4 possible outcomes. So here is a table with Z1, Z2, and the Z2, Z3. So Z1, Z2 can take value +1 or -1, and the Z2, Z3 can take value +1, -1. So these are 4 possibilities. And if you're in the logical state, you'll find that the Z1, Z2, Z2, Z3, they're always equal to +1. And if the third qubit has a bit flip, it would not change the outcome of Z1, Z2, but it will change the outcome of Z2, Z3. If the first qubit has a bit flip, then Z1, Z2 will be -1. If the second qubit has a bit flip, then both Z1, Z2 and the Z2, Z3 will be -1. So notice that these 4 possibilities of outcomes of Z1, Z2 and the Z2, Z3 will unambiguously identify the 4 possible cases of no bit flip or individual bit flips of one of the 3 qubits. So this gives an explicit procedure that if we can measure such an operator, product of Z1 and Z2, and product of Z2 and Z3, we will be able to unambiguously resolve which of the 4 subspaces the system is in without disclosing what is the logical information encoded in the system. And this is a key difference between quantum error correction and classical error correction, because we're not looking into individual qubits, we're actually performing collective measurement to get the error syndrome. Okay, so that achieves kind of like a syndrome extraction without destroying the encoded quantum information. So, or put another way, is that our logical space is actually a co-eigen state, co-eigen subspace of these operators Z1, Z2, and Z2, Z3 with eigenvalue +1, as shown here. And this will actually be extended to actually generalize to the stabilizer formalism, as you define a set of co-eigen commuting operators and find the co-eigen subspace, which will be used for your logical operations. And that's actually crucial because you can measure those commuting operators and without disclosing what's the encoded information, but at the same time identifying like what's the error has happened to the system. All right, so far we talked about the bit flip error. And what about the defacing error? Because that's also another error, which in practice is actually more common than, more dominant than bit flip errors for platforms like trapped ions and so on. So first, the defacing error actually is essentially implementing a Z operator to the qubit. Or maybe you can think it as a randomly performing identity or performing Z over the system. So if a Z operator is applied, then basically the superposition of a 0 and 1, there will be an extra minus sign applied associated with the coefficient of the one state. So the way to suppress the defacing error is actually use the following property. So you actually encode the information since, and so one way to think of it is that you try to catch the defacing error by using the property that defacing error, if the C0, C1 are equal to 1 over square root of 2, then that corresponds to the plus state. And under the defacing error, the plus state will go to the minus state, go to something completely orthogonal to what you start from. And this behaves very similar to the bit flip error acting on 0 or 1 basis. And here, it's actually easier to consider in the plus or minus basis when we have defacing error. So the idea is to encode the logical 0 to be plus, 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 and logical 1 to be minus, minus, minus. So if a defacing error applied to the plus state, it will give you minus. And if defacing error applied to the minus state, it will give you plus. So this effectively flips the error in the plus or minus basis. Now, what is our goal in terms of error correction of defacing error? First of all, we are not going to correct all possible defacing errors. We're actually correcting the most common ones. So suppose the defacing error happens independently for individual qubits, then the dominant defacing errors will be kind of the situation if no error happened, or maybe at least, or like up to like one of the qubits that has defacing error. So those are the 4 operators that we should focus on. And we are actually ignoring the other 4 operators associated with the pairs of qubits may have defacing error, or all 3 qubits have defacing error. But let's just ignore them because in principle, we can treat them as higher order processes that's less likely compared to the dominant ones we are considering. So now the error correction actually similar to what we have for the bit flip, but the only difference is that now it's a defacing error rather than bit flip, and we're actually using the plus or minus basis rather than 0 or 1 basis for the bit flip. So the error correction works as follows. So kind of to visualize what's going on, we can divide the entire 8-dimensional Hilbert space associated with the 3 qubits into 4 subspaces, while each subspace has a 2 dimension. So we can again call this to be the P0 subspace with no defacing error, and that's the P1 subspace with defacing error for the first qubit, or the P2 subspace with defacing error for the second qubit, and the P3 subspace with defacing error for the third qubit. And it's easy to verify that all these P0, P1, P2, P3, they give orthogonal projections to the corresponding subspace. And similar, like for the bit flip errors, here for defacing errors, we actually measure kind of basically swap between X and Z. So over there, you're doing Z1, Z2, Z2, Z3, and here we're actually measuring x1, x2, and x2, x3. First, you can verify that these two operators, they commute with each other. So the order that you measure them doesn't matter. Moreover, you can verify that measuring these two operators, it does not tell you whether it's logical 0 or logical 1. Because if you look at the logical 0 state, x1, x2, because plus states are eigenstates of x operator with eigenvalue +1. So this actually gives you, it's an eigenstate of +1 for x1, x2. Similar, if you look at the logical 0, which are minus, 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 but minus are the eigenstate of x operator with eigenvalue -1, but you have two x operators acting on the minus, so you get -1 squared. So this actually minus, minus, minus is also an eigenstate of the two x operator product with eigenvalue +1. So you can verify that for logical operators, either logical 0 or logical 1, they all have +1 eigenvalue for x1, x2, and x2, x3. Now, you can also check the other logical subspace with, if the third qubit has a defacing error, then it will change the measurement outcome of x2, x3, but not change the outcome of x1, x2. If the first qubit has a defacing error, it will change the outcome of x1, x2, but not x2, x3. If the second qubit has a defacing error, then actually that defacing error anti-commutes with both x1, both the first operator you're checking or the second one. So it actually, the value both gets to -1. So this actually allows you to catch the error and distinguish which error has happened up to a single qubit defacing error. Okay, so now we talk about the error correction for bit flip and the error correction for defacing. And in reality, we know that actually the errors could be both bit flip and defacing. And that actually inspired Peter Shor to come up with this 9-qubit code. So in order to correct bit flip and defacing both of those errors, the idea of Peter Shor's 9-qubit code is actually to do concatenation. So basically, you want to have two layers of code. So for example, the first layer, say, correct the bit flip, while the second layer corrects the defacing. So the first layer will suppress the bit flip to second order, and hopefully the second layer will suppress the defacing to second order. So therefore, you can suppress both bit flip and defacing to second order using such a concatenated code. So here is actually the code word, which is actually a bit long, but let me explain what the idea is. So first of all, it's a 9-qubit code, and the logical 0 consists of 3 blocks. Each block consists of 3 qubits, which actually encoded in the repetition code associated with the 000 and the 111 basis. So that's the first block. And there are 2 more blocks to make a 9-qubit. And the other 2 blocks essentially is the same as the first block, except it's just using extra 2 pairs, extra 6 qubits associated with those 3 blocks. So that introduces the redundancy at the second level, which actually allows you to suppress the defacing error. Okay, but before we get to the second layer, let's first look at the first layer. With this repetition code, in the first block, it can correct any bit flip error associated with the first 3 qubits. With the repetition code on the second block, it can correct the bit flip error associated with the 4th, 5th, and 6th qubits. And similarly, with the repetition code in the last block, it can correct any bit flip error associated with the last 3 qubits. Okay, now how do we, similarly for logical 0 or logical 1, they're doing the repetition code. So therefore it can, both of these code words has a capability to allow you to correct the bit flip error for any of the qubits. Now, what about the defacing error? First of all, defacing errors will not be corrected at that first level if you're only looking at individual blocks. You actually need to look at all 3 blocks. So what's happening is that if there is a defacing error, then this 0, 0, 0 plus 1, 1, 1, if there is a defacing error happens to any one of the 3 qubits, it will become 0, 0, 0 minus 1, 1, 1. Okay, while the other 2 blocks, since we only care about a single defacing error, the other 2 blocks are not changed. So at the second layer, you'll find that actually between these 3 blocks, actually one of the blocks will be different from the other 2. And then you can perform similar ideas of doing the majority voting to reject the blocks that disagree with the other 2 so that you can correct the defacing error. Okay, so that is actually the idea of doing the concatenated coding, so that at the lower first level, you correct the bit flip. At the second level, you correct the defacing. And that gives you the coding that the Shor kind of come up with to correct those errors. So here's the illustration if you want to correct, and the way to actually identify whether or not the first qubit has a bit flip, it's basically measuring Z2, Z3, and the Z1, Z2, and Z2, Z3. You will find that actually the measurement of Z1, Z2 will give you a minus sign indicating the first qubit has a bit flip. And how do we detect the defacing error? Is actually design a set of operators called the Z1, X1, X2, X3, X4, X5, X6. It's a product of 6 Pauli operators. And if there's a defacing error happen for the first or in the second blocks, you will actually find that this operator will give you a minus sign. That indicating that there is some defacing error happened in the first or second block. But to resolve the ambiguity, you actually need another measurement associated with the X operators in the second and third block. And if that outcome is plus sign, that indicating the second and third blocks are fine. The error is actually only happened in the first block. So that indicating it could be Z1, or could be Z2, or could be Z3. So this actually needs to kind of a natural kind of a feature of this code is actually there is no way for you to identify whether the first qubit or the second qubit or the third qubit that has gone a defacing error, because based on these measurement outcomes, they all look the same. Okay, so this is actually a property called the Degenerate Code, but actually, which is also unique for quantum case because there's no classical correspondence. However, this is actually something that doesn't matter, because if you misidentify the Z1 error as a Z2 error, what happened is actually you apply, if Z1 error happened and you thought it's a Z2, then you apply a Z2 correction. So overall, the system undergoes the evolution of a Z1 times Z2. However, the Z1 times Z2 is actually the operator, which for the logical space, it should be equal to +1. So therefore, that induces a trivial evolution to the system. So therefore, with the ambiguity of which error happened, but if you misidentify them, it doesn't introduce any of the error, then actually we can live with it. And this is actually the key idea of kind of the degenerate code, but I guess that maybe for the sake of time, I may not get too detailed further into this case. But the degenerate code is actually very interesting, related to like other applications of like a surface code and or like other more efficient code design. Having the degeneracy actually allows you potentially to encode more quantum information so that you can actually like reduce the physical resource overhead. So so that actually like covers the part associated with the introduction of the quantum error correction. So I guess it's probably a good time if there are questions that if the moderator thinks that I should answer, or if not, I will move on to the next section.
Hi Liang. So there are a lot of questions regarding the correction for the non-Pauli errors.
Okay.
So comment on that.
Yes. So good question. So actually, in practice, there could be errors which like sigma minus, right? Which corresponds to you go from the excited states to the ground states. Okay, and this here I'm using the basis of the first to be ground, the second to be the excited states. And this operator, you can also write it in terms of Pauli X. and poly y, which will look like minus I, 0, 0. So this operator, sigma minus equal to 1/2 sigma x plus I sigma y. You can verify that the off-diagonals term 1 plus I times minus I is equal to 2, and divided by 2 is 1. While the other off-diagonal terms will cancel. So this sigma minus, which is definitely not a poly error, it can be expanded as a linear combination of poly errors. Okay, as I mentioned earlier, you can think it as a superposition of poly errors. But when you do the error correction, it actually collapses to one out of the two poly errors, so that destroys the superposition, so that you'll get either one type of error or the other type. So as similar for the Shor error correction. So you basically will identify either bit flip or defacing error, or maybe kind of like a superposition or both bit flip and defacing error. So in that case, you can resolve them and correcting them without ambiguity. Or just to clarify this sigma y, you can also think it as 1/2 sigma x minus sigma x sigma z. So for this case, it corresponds to the only bit flip error. And for that case, it corresponds to, you see, both bit flip and defacing error, but each of which will be corrected at the corresponding level of error correction. I hope that answered the question in terms of you may have non-poly error, but it can be decomposed into poly errors, and then the error correction will kind of individually resolve those different poly errors. Yeah. So if there are no further questions, then I will move on to kind of the next topic, which is the quantum error correction criteria. All right, so previously I talked about the special case of bit flip or defacing error, and we can concatenate them to correct the errors. But actually, if you want to consider a more general design of quantum error correction, you probably may want to include the possibility that you may simultaneously correct bit and defacing errors. And maybe there's no need to separate these into two layers of encoding. Okay, and also later on, we'll also talk about the bosonic quantum error correction, which is not just as qubits. It may have like maybe loss, photon loss, or photon defacing. So therefore, for those codes, we actually would need to have a more general formalism, not restricted to quantum bits. So this actually motivates the design for quantum error correction. And we want to have a general, hopefully necessary and sufficient criteria for designing quantum error correcting codes. So in order to design quantum error correcting codes, one thing is that, okay, of course, it will be convenient if you can specify the logical basis for the codes. And sometimes that choosing the basis might introduce some ambiguity, which one you like to be 0 or logical 0 or logical 1. But actually, all that matters is actually the projection to that code space that in some sense already uniquely specified your quantum error correcting codes. Whether which one to be logical 0 or which linear combination to be logical 1 is actually your choice. But once you fix the projection, in principle, you already fix the code. Okay, now, so when you talk about quantum error correction, we want to talk about two things. One is, what is the code space? The other is, what are the errors that you want to correct? So similar, again, we're not going to correct all possible errors. We're only going to correct the dominant errors. So now let's suppose that the notation-wise is a bit conflicting here. So here I'm just write this math cal epsilon as a kind of the quantum channel, which acting on the system, which can, as discussed in the first lecture by Daniel, that you can always write a quantum channel expanded in terms of cross operators. So this is actually the cross operator representation. which you can see in Monday's lecture. And so once we have these cross-operator representations, and we will have these cross operators. And suppose this is actually an error channel, we want to have a full quantum error correction, then basically we should have a way to describe what are these cross operators should satisfy in order for our error correction to overcome such cross operator errors induced by these cross operators. All right, and the answer is actually a very concise statement as shown here, which we call it actually the quantum error correction criteria, which is a necessary and sufficient condition for a given quantum code to correct the sets of errors. So the condition only depending on kind of the choice of the code here, actually in this statement using the code words, and the cross operators associated with your errors. Okay, so, and the condition is just the one line, which is on the left-hand side, it's basically saying that you are sandwiching, you kind of like considering kind of some overlaps between the error EJ acting on code word phi L with another state, which is associated with error EI acting on the code word phi K. And the overlap is actually a 4 tensor, which depending on indices of KL and the error labels I and J. And this general 4 tensor can be decomposed into a product of 2 tensors. Generally, it's not true, but for this case, you actually require the 4 tensor to be decomposed into this product of 2 tensors. And the 2 tensor has a property that the indices associated with the code word K and L, they should be proportional to identity. And the indices associated with EI, EJ, it's actually Hermitian, and it's a Hermitian matrix. And once this condition is satisfied, basically saying that 4 tensor can be reduced into a product of 2 tensors, then you actually can satisfy the quantum error correction criteria. Now let's actually interpret what's going on. So the condition of delta KL, which says if the code words L and K, if they are already orthogonal code words, then after this error applied, they should still remain being orthogonal. Okay, so that's actually a very natural condition. And if you think about what we do with the repetition code, with phi 0 being all 0, phi 1 being all 1, and the errors we want to correct, the cross operators of correctable errors associated with are spanned by kind of these poly X on individual qubits or identity operator. Now let's consider the case that suppose that we have phi K, phi L, let's say phi K is all 0, phi L is all 1, and we're just flipping 2 out of the 3 polys, and there is no way to make an overlap, finite overlap between phi 0 and phi 1 by just flipping 2 out of the qubits, because they differ by 3 sides. So therefore, this condition guaranteed to be 0 if K and L are different. So that indicating there is no mixing of different code words induced just by those error operators. So that's the condition, which is saying like, okay, this part of the condition. Okay, so if the code words are the same, phi K, phi L are the same, then it's possible that they will give a good overlap. For example, they have both the same code word undergo same error, then the overlap definitely will be finite. Okay, and for this case, you can actually check what the matrix associated with alpha ij. And it turns out to be, it's actually diagonal, because you can think that the errors will have maybe bit flip of 1, 2, 3 qubit, or no bit flip. And the only if you start from the same, in order for get alpha ij, you need to set the phi K, phi L to be the same. And the only way for the EI, EJ operating on the qubits, operating on the logical state to have a finite overlap is actually the Ji and the J should correspond to the same qubit. So therefore, that alpha ij actually has this diagonal form, which is consistent being a Hermitian matrix. So that is actually just an illustration of this error correction criteria. Now, let's actually think more kind of pictorially what's going on. Now, suppose this alpha ij is actually in the diagonal form. Then what it means is that basically you will start from some original logical space, as we previously called the P0 space. And then the error E1 happened, it actually mapped it to the P1 space. And the error E2 happened, it will map it to the P2 space, and so on. And this actually can be can kind of generally exist if for the case where alpha matrix is diagonal. And later we'll talk about there's always a way to diagonalize alpha so that this mapping in principle holds quite generally for error correcting codes. And the condition of delta ij in the error correction criteria, indicating if you have a state, say phi1 as a logical state, and a logical state phi2, they undergo different errors. These states should always be orthogonal. Even if they undergo the same error, they should also remain orthogonal. So therefore, that's actually what this kind of theorem, error correction criterion tells. Two ingredients. Different errors kind of, and for alpha ij being diagonal, will actually map to different subspaces. And the orthogonal states should remain orthogonal. So therefore, that actually enables, you can always come up with some projection to different error space and then perform a unitary to map everything back to the logical space. So that's kind of like a more like intuitive proof for the error correction criteria. Okay, so I think that's maybe there is actually important statement related to actually the question at the end of the last section as well, is that so far I treated those error or the cross operators as a discrete set of cross operators. And it turns out that any linear combinations of those operators that the error correction can correct can also be corrected. So suppose instead of like writing the set as a set of EIs, I can write a set of GMs where GM is a linear combination of EI. Then in this case, one can find that the error correction condition previously was written in terms of EIs being proportional to alpha ij delta KL. Now, if I write that the same expression, but replace EIs by my GM and GN, you'll find that this expression is actually, again, some linear combination, some like a sum over like ij, which are the indices associated with EIEJ, but with a coefficient fmi and fnj. Once you did that summation, you'll find, first of all, the delta KL doesn't depend on the summation, so it still stays here. While alpha ij, after the summation of the fmi and fnj, it gives me another coefficient, which is called beta mn. And that coefficient, the matrix associated with it, is again Hermitian. So therefore, if I have the error correction criterion satisfied for EIEJ, then the same criteria should also satisfy for GM-GN, which is a linear combination of EIEJs. So therefore, error correction, it's actually easier. You just need to check some basis operators, then any linear combinations of those operators, so guaranteed it can correct those errors. And related to that previous question, that if we know if errors of poly X, Y, and Z can be corrected, then the X plus IY, which is the linear combination of those errors, can also be corrected. So this is actually very helpful because we don't need to check our infinite possible decompositions. All we need to do is just find some basis operators that we can correct. Moreover, for qubit case, that immediately implies we only need to consider correcting X, Y poly errors for qubits, because for individual qubits uncorrelated errors, then that actually will be sufficient because we just need to make sure like the sufficient number of qubit errors up to a certain number can be corrected. And any linear combinations of those qubit errors will also be guaranteed to be corrected because of the statement of linear combination of error will guarantee to satisfy the error correction criteria. Okay, so therefore, like any individual qubit errors, which can be written as linear combinations of poly X, Y, and Z and identity, then we can actually come up with for n qubits, it will always be some tensor product of these any individual qubit errors. Then you can actually write it as a linear combinations of individual Pauli operators, and the error correction will project it into a discrete sets of errors. And therefore, we can have a very concise statement and also design for quantum error correction. So I think that probably like maybe for the sake of time, I may not go into details about the proof of this error correction criteria. But if people are interested, I would kind of like refer it to the notes, which I outline the detailed proof. And moreover, I would refer it to like a Niels and Chuang's textbook, which also actually like give a very like a rigorous derivation of the quantum error correction criteria. So maybe before I move on to the next topic, maybe are there any questions that maybe I should address?
So far, there are no questions regarding this this section.
Okay, good. So maybe just to remind everyone, all we need to remember is just for this section is just this expression of error correction criteria. Okay, which says that the error operators sandwiching by different states have this property. And moreover, sometimes that people may write this criteria in a slightly different way. So for example, you may put in a different psi k on the left and put in the psi l on the right. And on this side, you also have psi k, psi l. Okay, then you sum over k and l. And here you also do the summation over k and l. And what you get for the left-hand side, here you sum over psi k projection. So that gives you this projection of the code word. And then you have the EI dagger, EJ. Again, the projection of the code word, which is associated with the sum of L, psi L, psi L. And on the right-hand side, you first get the alpha IJ, which is independent of the summation. Then you do the summation over the K and L with the psi K, psi L with delta KL. So that again gives you the projection of the code word. So this gives you another way of writing the error correction criteria, which in terms of just the projection of the code word. And there is no dependence of how you write down the psi K, psi L. And that actually like, again, kind of verify the previous claim that actually the choice of the code word actually doesn't matter in terms of the error correction criteria. And here I'm just deriving it from the base dependent form to the base independent form. You can also show it backwards by multiplying the state of phi k from the left and the phi l from the right. Okay. And you'll find that you can restore the original form of the error correction criteria. So therefore, this condition is actually equivalent to the basis dependent expression. So that's actually like it's sometimes depending on how you want to use it. Sometimes it's convenient to use the basis explicit form, or sometimes it's convenient to use the base independent form. Okay, so this is just like another commenting case. People wonder like, oh, okay, what kind of the choice is the basis that one may need to use? And actually for our error correction criteria, in principle, there is a way to write it in a base independent form. Okay, so now it's actually maybe a good time to think about how we use these error corrections to actually design some other error correcting codes. So a very common code that people use for qubit-based error correction is called the stabilizer quantum error correction. So as I already mentioned earlier, that we can try to come up with some like commuting operators, which which we actually call classical error correction, corresponds to called check or syndrome measurement. And in the quantum case, we actually call them the stabilizer operators. So because these operators, they commute with each other, there's actually a possibility of measuring all of them without kind of like modify the other operators. And so a typical type of stabilizer operators is actually here we're restricting to kind of like a product of Pauli operators. Okay, so there is something called a Pauli group, which is basically spanned by like all the Paulis you may have and tensor A. And sometimes you may attach a ±1 and the ±I just to make sure the product operation is closed. So maybe let me just make sure like everyone on the same page. For the group, the mathematical definition for the group, it has 3 properties. It should be closed under multiplication. If there are 2 group elements G0, G1, G2, the product of G1, G2, it should be also in the group. And the associativity is that G1 times the product of G2, G3 should be equal to the product of G1, G2, then times G3. And the inverse of any group element should be also in the group. And here, for our case, if we think about the Pauli groups, then Pauli operator products should also be in the group, and the ordering of the multiplication actually should give you the same Pauli, and the inverse of the Pauli is itself. So therefore, actually, it is indeed forming a group. Okay, so now we have this Pauli group, and the Pauli group, the elements in the Pauli group has the property that any element square should be equal to +1 or -1. And the elements in the Pauli group will be either commuting or anti-commuting. And the Pauli group and the elements itself is its own inverse. So therefore, actually like this forms kind of a general properties for the Pauli group. So now one important property is actually the Pauli operators. If you have 2 Pauli operators, they will be either commuting or anti-commuting. There are no third possibility. So therefore, that actually makes analysis simple. And later we'll see, like if you have errors which commute with your stabilizers, then you probably may not be able to detect such error. If you have errors which anti-commute with the stabilizers, then actually you will be able to detect the error. So this is actually like a very useful in terms of actually like analyzing like whether or not you will be able to detect the error if you're thinking about the error being a Pauli element and the stabilizer also being a Pauli element. Okay, so now actually like in order to proceed, and we may notice early on when we try to write down the 9-qubit shortcode, the code word is already getting very, very long. And generally, if you have n qubits, you probably may need to write up about the 2 to the n terms. So it's actually very inefficient to write down the code words explicitly. So instead, actually a good way to do it is to write the stabilizer operators rather than the code word, because you can actually have an efficient way to write down the stabilizers, which instead of writing down the state explicitly, we write down a set of operators, say that the state is a co-eigenstate of those sets of operators. Okay, so for example, like we talk about the repetition code, 0, 0, 0, 1, 1, 1, right? So for the repetition code of 0, 0, 0, and 1, 1, 1, of course, here it's a 3 qubit, so you can write it very easily. But the alternative way to write it is saying that it's actually a co-eigenstate of these sets of operators, which is O identity, or Z1, Z2, or Z1, Z3, or Z2, Z3. So once you write down these operators, you can specify that it is uniquely like the co-eigenstates will always be some linear combinations or mixtures of all 0 and all 1 states. So that actually motivates us to define such an operator we call the stabilizer group. The stabilizer group is actually a subgroup of the Pauli, and all the elements as illustrated here, they commute with each other. And the commuting is important because we want to have co-eigenstates of these operators. Okay, And the stabilizer group, actually you'll find that any element in there, the product of them is also in the elements. So therefore, actually you can further reduce it. Instead of writing down all the elements, you just say, let's find the generators for stabilizers, which is the minimum set of operators that can generate the group. For example, here we can write it as Z1, Z2, or Z1, Z3. Now, the product of the operator itself with itself will actually naturally give us the identity. And now the product between these two, you'll actually get a new one, which in this case, it corresponds to Z2, Z3 when you multiply in the product of these two. So therefore, this gives you a way to generate the entire subgroup associated with this set of stabilizers. So notice that if you have like more and more qubits, the elements in the stabilizer group may grow exponentially, but the generators for that group will only grow linearly with the size of the system. So that gives you an efficient representation to write down or constrain what the code word will be. Okay, yeah. So that actually gives us an efficient representation that grow only linearly with the system size rather than exponentially with the system size. And that's actually very efficient, very important if we want to design larger scale quantum error correcting codes. So now, since we have these stabilizer group, which consists of operators commuting with each other, so we can actually define a stabilizer subspace. So what is a stabilizer subspace? It is a subspace of the entire Hilbert space, which is the eigenvalue +1 for all the stabilizers inside the stabilizer group. Since all the stabilizers in the stabilizer groups, they commute with each other, so it's possible to conceive that maybe we have some states or some subspace which are co-eigenstates of these stabilizer operators. And here, for convenience, we actually require it to be eigenvalue +1 so that any product of the stabilizers in the stabilizer group will also guarantee to have eigenvalue +1. Okay, so just think about it, that now suppose we have a stabilizer group, for example, in this case, which is generated by two Pauli operators. And each Pauli operator may have eigenvalue +1 or -1. So if we restrict it to be in the stabilizer subspace with eigenvalue +1, then each of these Pauli operator will reject about half of those Hilbert space. And since we have two, then only about a quarter of the Hilbert space associated with the entire Hilbert space will make these two stabilizer generators happy with eigenvalue +1. So therefore, if we have a system with, say, R stabilizer generators, then there's only a fraction of 2 to the minus power R, or 1/2 to the power R of the Hilbert space that will be able to actually fulfill the requirements of stabilizer being equal to +1. Okay, so basically that's the dimension of the Hilbert space. So the dimension of the stabilizer subspace will actually decrease when you put more and more stabilizers into the stabilizer generator. So if you add one more stabilizer to the stabilizer generator, the dimension of the Hilbert space in the stabilizer subspace will reduce by a factor of 2. So here, if you have a minimum set of R stabilizer generators, then basically the dimension of the stabilizer subspace will be decreasing as 2 to the power -R. Since the starting point, if you have n qubits, is 2 to the n, when you have R stabilizer generator, then the dimension of the stabilizer subspace is actually 2 to the k, where k is equal to the total number of qubits minus the number of stabilizer generators. And that gives you the number of degrees, the dimension of the Hilbert space, which is 2 to the k, which if we take a log base 2, that indicates the number of logical qubits. All right, so now let's look at the example. If we consider the repetition code, again, we have two stabilizer generators, however, which is R equal to 2. And the repetition code has 3 qubits, so n is 3. So m minus r, which is 3 minus 2, equal to 1, that indicating that we have one logical qubit encoded in this particular coding. That gives us a 2-dimensional subspace for our logical operations. Okay, so now we talk about the stabilizers, and we also want to, and that might be able to help us to correct errors, but we also want to find operators associated with the logical operations to help us to process information. So now we need to define the logical operator. So what is a logical operator? So the logical operator should satisfy the condition that you need to commute with the stabilizer, because otherwise that operation will push the system out of the code space. So that's probably not desirable. And also need to have some non-triviality in the stabilizer subspace so that it will induce some a non-trivial evolution in the code space. And it turns out that you can always come up with a set of Pauli operators in terms of product of individual Paulis. We can come up with, if there are k logical qubits encoded, where k is m minus r, then you can come up with, for each of the logical qubit, you can come up with a pair of logical operators we call logical x, logical z, that allow you to do the operation associated with that particular logical qubit. Think about the trivial case when r equal to 0, then k equal to n, then you can think that x1, z1 just the acting on the first qubit, x2, z2 just acting on the second qubit, and so on. But now the non-trivial case is actually when r is finite, then these x and z's may not necessarily be associated with individual qubits. It may associate with the product of Paulis or multiple qubits, allow you to process the logical operations. So we'll show more examples of these logical operators in a moment. But here I just say that there exists such a solution, enable us to do logical operations. So now let's actually think about, okay, now we have these sets of stabilizers, and how do we use it to actually detect and correct errors? So first of all, let's just think about, we may have Pauli errors. So these cross operators may be Pauli. So the product of those cross operators of E, I, E, J is also a Pauli operator. Okay, so now it's actually maybe a good time to remind ourselves about the error correction criteria. So just to recall the error correction criteria. It's basically, we have logical state phi k, phi l, sandwiching the ei dagger ej, and it should be equal to alpha ij delta kl. All right, so let's check actually whether or not the certain set of errors will be able to satisfy the error correction criteria. And if it can satisfy, that indicating that indeed we can correct those errors. Right. Sorry about that. Just a second. So now, in terms of the, so we're thinking about the errors, which actually will be a Pauli operator. And now it's actually this notation P is for Pauli, not for projection. Sorry for confusion, but let's just keep in mind that this P is actually associated with the product of Pauli errors. Okay, and so itself is a Pauli. And also our stabilizer generators are generally just denoted as G, as one of the generators in the stabilizer group. So the G, it will have two possibilities in terms of the relation between the Pauli and the stabilizer generator. They may either be commuting or anti-commuting. Okay, so if they're anti-commutes, it means that the P times G equal to minus G times P. So that indicating that actually the order, whether which one acts first, matters. Okay. Moreover, this G is a stabilizer generator. So basically the G acting on any state phi L is equal to phi L, because the logical state is the eigenstate of the stabilizer generator with eigenvalue +1. Okay, so now let's check. Let's plug this P, which is EIEJ, into the error correction criteria at the left-hand side. So psi K psi L sandwiching this EIEJ error, which is a poly P. And since psi L is the eigenstate of the stabilizer generator G, we can put in the G inserted into here. And then we can anti-commute G and P, which gives us the extra minus sign because they anti-commute. And then because they anti-commute, you can actually proceed further and absorb this G to the phi K, simply because phi K times G equal to phi K. All right. So therefore, we obtain the final expression, which is phi K P phi L being equal to phi K P phi L, but there is an extra minus sign. So what does this mean? A number is equal to its own negative. That means that this number you're considering is actually equal to 0. So that means that in terms of error correction criteria, that this quantity is equal to 0. And 0 means it's actually just set alpha ij equal to 0. And regardless of delta K and L, this condition is always satisfied because you can just assign alpha ij equal to 0, then you will satisfy this condition. So therefore, that implies that actually error correction is satisfied. Okay, so therefore, that actually shows that if you get some error operators EIEJ, if their product gives a poly that actually anti-commutes with any of the stabilizer generators, then you're in a very good situation because you can correct that error. So that is the really favorable case that you can correct those errors. Okay, and actually in our first homework problem, that you'll find that I'm asking you to see whether or not that a 5-qubit code can correct single qubit errors. And the idea that's showing here is actually to see if you can come up with listing all possible poly operators associated with errors you want to correct, and make sure that there always exists one of the generators in the stabilizers to be anti-commuting with any of the polys associated with the errors you want to correct. Then you can show that actually that error correcting codes associated with a set of stabilizers can correct all those sets of errors. Okay, so this is so far I would say the simple case, which actually the errors, the poly associated with the error is actually anti-commuting with the stabilizer, but it may actually commute with the stabilizer. And then there could be two cases. So one is actually that poly is in the stabilizer group. Then it definitely will commute with all its elements. If that's the case, that's actually, again, a good situation, because when you apply that poly acting on different, acting on the qubit states, and acting on logical state, because it's in the stabilizer group, it has eigenvalue +1 acting on the logical state. This is guaranteed to be equal to delta KL. That implies actually alpha JK is equal to 1. And then that naturally satisfies the condition. So therefore, that actually is also a correctable error. And this is actually correspond to the case that we talked about in the 9-qubit code. This actually corresponds to the degenerate error case. All right. So now, I think that's maybe the two cases that actually the error correction can correct those errors for our stabilizer codes. And there are also an unfortunate case, which actually, if the P commutes with all stabilizer generators, but not in the stabilizer group, then that corresponds to the case that actually it will be an error that you cannot correct. if P PG equal to GP and P not in S, then that actually corresponds to uncorrectable errors. Because actually this may lead to kind of like a logical operators. It could be logical operators. Okay, and a good design of error correcting codes is actually to design a set of P so that we will be able to design a set of stabilizers so that we'll be able to identify those and to have a larger set of correctable errors in your set. Okay, so now let's actually look into some of those code designs. So here are some like examples of stabilizer quantum error correcting codes, and some of them we've already seen. So the first example is a 3-qubit qubit flip bit flip code. The stabilizers is Z1, Z2, and Z2, Z3. And you have n qubits, 2 stabilizer generators, and n minus r equal to k equal to 1. And you can come up with the logical operators which commute with the stabilizer generators and they anti-commute with themselves. So that gives you a definition of the logical Pauli operators. And notice that these logical operators, the way you write them is not unique because you can always multiply them with a stabilizer generator. And what happened is that ZZZ multiplying the G1 will give you Z3, which means instead of applying like 3 Paulis on the 3 qubits, you can simply apply a Z3 acting on the 3rd qubit, then you will be able to implement the logical Z operation. Okay, so, and you can verify with the criteria saying that actually the G1, G2, they will be anti-commute with any linear combination, or any like a kind of like EI dagger EJ from these sets of errors so that you will be able to correct the corresponding error. And similarly, we talked about the 3-qubit phase flip code, which the code word is here, but here now we try to get familiarized in terms of stabilizer, and this corresponds to XXX, X1, X2, or the X2, X3. So those are the stabilizer generators, and the logical operators are just, again, product of all Pauli X and the product of all Pauli Z. And you can verify that for the errors from this set, when you compute the EI dagger EJ, it will be anti-commuting with these stabilizer generators. And similarly, you can check the 9-qubit code. And for the sake of time, I probably will not go into all the details here. So maybe one code I would like to bring your attention to, which is actually the 713 code, which is using 7 qubits to encode 1 logical qubit. And this code, actually you can have, since n is 7, and you want to encode 1 logical qubit, k is 1, so you need r equal to 6, which is 6 stabilizer generators. And you may notice that the 6, you can group them into 2 groups. Each group will have 3 such stabilizer generators. And the first group only consists of Pauli X operators, and the second group only consists of Pauli Z operators. And these groups are actually very similar to each other. Just by switching between X and Z, you will actually kind of like a map between these 2 groups of stabilizer generators. And so notice that in this case, for the 713 code, actually all you need to specify is just write down these 6 stabilizer generators instead of writing down such long states with many, many terms. So that indicates that actually when you get a larger code, you get a kind of like only like a linear complexity to specify the code, while you'll get the exponential complexity if you write down the code words explicitly. Okay, so that I hope that gives you some feeling about what kind of like stabilizer codes we may have. And then there is actually kind of like a certain, all the codes we've talked about It belongs to a class called the CSS code. So it actually naturally established the connection between classical error correcting codes and the quantum error correcting codes. So basically, the essence of CSS code is saying if there's 2 copies of classical codes which satisfy certain condition, you can put them together. That can give you a good quantum code. And here, like for the 713 code, that the stabilizers associated with all X, it's actually correspond to one version of a classical code, and here is another version of classical codes, and you put them together, that can give you a good design of quantum codes. And sometimes CSS codes are favorable, is because in terms of logical operations, because all the stabilizers and also logical operators consist simply of product of poly X and poly Z, it will make it easier to detect the syndromes and also make it easier to do quantum gates such as transversal gates. And now in the first homework problem, we actually have a 513 code, which is showing here. Okay, so the stabilizers are these 4 poly operators. And notice that it's a mix of poly X and poly Z. Okay, so this 513 code is not a CSS code. And there's no way you can write it and separate X and Z operators. However, it actually gives you a more efficient encoding because think you only need 5 qubits to encode 1 logical qubit. And here, the third number 3 indicating it's a distance, which is saying the minimum number of polys that you need in order to come up with a logical operator. And for this 513 code, you will find that actually a simple way to write the logical is the product of all poly X's. But when you multiply that with the stabilizer generator G1, you actually get an operator which is identity, Y2, Y3, and X5. So it's actually a poly, it's a weight 5 poly that corresponds to this number, which is called distance. So distance has 2 meanings. One meaning is that it's a minimum weight of poly that you need, which corresponds to the maximum erasure you can tolerate. Because if 2, 3, 5, those 3 qubits are being removed, then you will not be able, the actual environment can get some information about this particular coding with X bar. So that's kind of the maximum erasure one can tolerate with this code. And moreover, if it's a distance minus 1/2, that corresponds to the unknown kind of like a poly error this code can tolerate. So, so distance D here, it has a meaning which is D is the number of erasure, and so the D minus 1 is the number of erasure the code can tolerate. And the D minus 1/2, it actually corresponds to the number of unknown poly errors the code can correct. So that's actually like depending on the error model. If you have erasure error, you would look into D minus 1. For this case, you can correct the 2 erasure error. And for the unknown poly error, which is more common, then this corresponds to D minus 1/2. In this case, it's equal to 1. So in principle, in your homework, you could say, look, I know the distance of the 513 code is 3, so D minus 1/2 is 1, so it can correct up to single poly error. However, that you may want to think about, how do we show that this code has distance 3? Okay, it actually may want to exhaust all possible like logical operators and verify that the minimum number of polys that you need to write the logical operator is 3. So that could be another way of solving the homework problem. So now actually like I think some of you might have a question that how we actually perform such measurement of stabilizers, which are product of polys. We know how to measure individual polys, but for quantum error correction, we cannot measure individual polys and then multiply them because that would collapse the quantum states. So that's actually like here is one of the very useful circuit, which is related to kind of the theme on this topic on the measurement and control. How do we measure the stabilizers? So the idea is the following. Every time we think about the measurement, you may think, oh, generally you can think about the POVM, generalized measurement. But here, actually, we're just thinking about the two projections. Suppose I want to measure a particular Pauli operator P. Okay, it could be product of small Paulis. Then instead of measuring individual Pauli components, I can measure it collectively. Okay, so for example, here on the circuit, what I'm showing is you have an ancilla which prepared in the plus state. And here the psi is actually consists of multiple qubits. Okay, and here the slash indicates that there are multiple qubits. And I have psi coming in, and the ancilla performs a controlled Pauli over the multiple qubits. And then I perform the measurement of the ancilla and in the X spaces. So the outcome will be either plus state or minus state of the ancilla. The claim is, if its outcome is plus, then actually I perform a projective measurement of this encoding block to the subspace where P is equal to +1. If the measurement outcome is minus, then the effect is I perform a projective measurement, and the effect of the back action to the system is actually that this system's output state is in the subspace associated with the eigenvalue -1 associated with this Pauli matrix P. Since Pauli matrix only have +1 or -1 eigenvalues, those exhaust all the possibilities. Okay, so that is actually how this circuit works. And effectively it implements a measurement, actually a projective measurement associated with these two measurement operators. And I think that there was some also mentioned, I think in Ivan Deutsch's class, he mentioned about the POVM, and a generalized measurement will consist of sets of measurement operators which add up to identity. And this is the POVM, with n plus correspond to 1 plus p over 2, and n minus, which is 1 minus p over 2. And whether you measure to be n plus or n minus, depending on this measurement in the X qubit, is in the plus or minus spaces. All right, so to convince yourself that this is the case, you can think it as this incoming state is just a single qubit. It's say like in the 0, 1 state, and the Pauli is a PZ, is a Z operator. Then you do this control phase, and if it's 0, if it's 1, it will actually induce an extra Z rotation on the control that will convert the plus to minus. So therefore, that indicating that that for this particular case with single Pauli, you're projecting it to the 0 or 1, depending on the ancilla measure to be plus or minus. Okay, so that's actually like this is a really useful circuit, because notice that there is no destruction of the system that we want to measure. Okay, we don't destroy any qubits in the system. We just have a single ancilla that tells us exactly one classical bit of information, that's whether the system is in the 0 plus, is in the +1 eigen subspace associated with the Pauli, or the -1 eigenspace associated with the Pauli. So it's actually something desirable, which I think in Ivan's class, he also mentioned this is a quantum non-demolition measurement. Okay, so now let's actually look into a bit more detail. How do we do a control Pauli where Pauli consists of product of Paulis acting on individual qubits? Then the circuit design is the following. Here is kind of a schematic, say I do a controlled Pauli over multiple qubits, but you can decompose into control Paulis acting on individual qubits. Okay, so that's actually the circuit design. But later on, for tolerance, this circuit may have its limitations, because if you have bit flip on any of in the intermediate steps, it may propagate to like multiple qubit Pauli errors. But this can be resolved if we have fault tolerant design. Okay, so I think that there are also variations of this like stabilizer codes, including like maybe we can generalize it to something called the subsystem code. And also like sometimes for these circuits, you want to reduce the number of Paulis you want to collectively measure. That actually favors a design for the quantum low density parity check code, quantum LDPC code. And recently, there is significant development in the quantum LDPC code in terms of the coding rate being constant, and the code distance can scale linearly with the size of the code. So I think that's also an interesting direction that you may want to keep track of. But for the sake of time, we're not getting into detail on this topic. Yeah. So I think it's also a good time to take a break, see if people have any questions. All right, so if not, then maybe I think let's maybe take a 5 minutes break, and then we'll come back in about 5 minutes. Okay, so maybe so Richard, shall I pause recording?
No, I think you can just let it go because they're going to edit it.
Okay.
And they'll edit the breaks out, is my understanding.
Mm-hmm. Yeah.
Yes, I can confirm.
Yeah. So Lang, I think it's also worth, so at the end of your lecture, I think it's worth either you or I or Brigitte can make the announcement about probably taking a 15-minute to 20-minute break after the end of your lecture, and then people can gather back, and we'll post the link to the Zoom, the Zoom room where people can participate, and then they can work on the problem sets. And then also important to announce that everybody is welcome to come back at the 1:30 time period into that same room for general Q&A, go over the problem sets and anything else they want to talk with you about.
Sounds good. So are you going to post the Zoom link?
Yeah, I'll post it at that time.
Okay, that would be great. Yeah.
Well, let me post it now and then we'll post it again. That's probably a good idea.
Yeah, thanks. Yeah, okay, so let's continue the discussion. So first, I would like to draw everyone's attention that actually Richard posted some links in the chat about and the later discussion and the Q&A session. And also like the lecture notes that are already uploaded to the course website so that you can just directly download them. Because we're actually covering a lot of materials, so it's probably more efficient to just like have the notes ready rather than just copy down everything. Yeah. Okay. So far we talked about like in the general error correction criteria and the stabilizer error correcting codes for qubit systems. And we know in practice there are also like other platforms that also needs error correction. For example, if we do quantum communication, we actually send the information over photons. And also there are also ways you process information in the bosonic systems. So that naturally leads to the question, can we protect the information stored in the bosonic system? And let's just recall that we have this very general, necessary, sufficient condition for quantum error correction. So that should not only apply to qubit systems, but also apply for bosonic systems. Just to remind ourselves, these phi L, phi K are logical operators. E, I, E, J are the error operators. And this product on the left will be a 4-index tensor, which will be decomposed as a product of Hermitian matrix and the identity associated with these two pairs of indices. Now, the again, the idea of quantum error correction is actually to introduce redundancy so that you can use that redundancy to help you to detect errors while without destroying the encoded information. For qubit systems, we're actually like only limited by a two-dimensional system for each qubit. So we basically need to have more qubits and to introduce redundancy. While for bosonic systems, we're actually in a much better situation because if you might remember from your quantum mechanics class, even with a single harmonic oscillator, it has many, many eigen energy levels. And in principle, we just need to encode a two-level system into this infinite dimensional, like a Hilbert space. Okay. For example, you can encode information with the lowest two levels. That's actually some of the codings that people use for the 0-1 encoding with minimum excitation. Or if you can encode the information with the 0 and the 2 photon states, then in principle, that allows you already to detect a single photon loss. Because if a photon loss happens, it will go from an even subspace with the even number of photons that you start from to an odd subspace with odd number of photons. And in principle, you can already detect such an error. However, that coding may not be so good in terms of correcting errors because once that happens, it's sort of the only way for photon loss is actually to go from 2 to 1. So that you know that the initial state has to be 2, and that collapses the states of the encoded information. So now the art of a design error correction is really to come up with a good choice of subspace so that the errors you want to correct can be suppressed or suppressed to higher order. And so here, for simplicity, let's focusing on the case that say there is no error or single photon loss error. And those are the errors we want to correct. And there's one thing that may be slightly different for bosonic system and the qubit system is actually for bosonic system, these operators is actually not a Hermitian operator. Okay, it's different from polymatrix because A and A daggers are different. Second is this operator may not necessarily be a unitary as shown here. So that's something maybe one should be careful when we actually like doing computations. So, but it's still like something that the general principle of error correction criteria still apply. So let's look at one example, which is called the Kitten Code. So Kitten Code is actually like a very interesting single mode bosonic quantum error correcting code designed by Steve Gerben. And the idea is actually to use a superposition of different photon number states to help you to correct photon loss errors. Just recall that the photon loss is an annihilation operator, which acting on n photon states will give you an n-1 photon states. And because of bosonic enhancement, you get a square root of n enhancement here. Okay. On the other hand, you also get this, if you apply a creation operator, which is a Hermitian conjugate of annihilation operator, you increase the photon by 1, while there's a bosonic enhancement of square root of n plus 1. Okay. But I guess for most of the discussion below, we just need the property of this annihilation operator. So now let's see what is the Kitten Code. How do we correct single photon loss just using a single bosonic mode and without leaking out what the encoded state is? So here is the coding. The logical 0 consists of equal superposition of 0 and 4. And for the convention, we choose the coefficient to be the same phase as well. It's a symmetric superposition. And the logical 1 is a Fock state with 2 photons. And one thing you can immediately notice is the average number of photons for both logical 0 and logical 1 is equal to 2, which indicates that to the leading order, they're both equal likely to lose a photon. Moreover, any superposition or mixture of logical 0 and 2 will give you 2 photons because they actually cover different spaces. So it doesn't matter what coefficient you put in the logical 0, logical 1, or even the mixture, there will be 2 photon states. So basically saying like, doesn't matter which logical states you have in the system, it's equal likely to lose a photon. So based on the likelihood of photon loss, the environment cannot infer which logical state it's in. So that's kind of like a intuitively understanding how this code can protect the photon loss, because there is no way for environment to infer which particular state that the system is in just by detecting a single photon loss from the events. So here is actually another perspective to see what's going on. And this is more from the system perspective. So if you have logical 0, logical 1, in the presence of photon loss, what you do is apply annihilation operator to logical 0, logical 1. If you apply annihilation operator to logical 0, the vacuum component will be annihilated. And if it's a 4-photon state, it will actually give you apply a logical operator, and this square root of 2 normalization factor is also important. And use bosonic, this formula, we will get the output will be square root of 2 times the 3-photon Fock state. On the other hand, if you from logical 1, which is a 2-photon Fock state, you apply annihilation operator, it gives you square root of 2 times the 1-photon Fock state. So 2 things to notice is the output will always give you odd number of photons, because when you lose a photon from the even photon subspace, it goes to the odd photon subspace. Second, the coefficients are the same, equal to square root of 2. And this is crucial if you want to preserve the encoded information. This is because if you start from any superposition of logical 0 and 1, if you lose a photon, then what happened is the square root of 2 factor, you can put it to the front, while the original coefficient C0, C1 will still preserve. But the only difference is instead of acting on the logical 0, logical 1, this time it's acting on the error state 0 and error state 1, which is 3-photon and 1-photon Fock states. Therefore, even it actually whole evolution doesn't depend on what exactly the values C0, C1 are. And you can always come up with a unitary to map the 3-photon Fock states to logical 0, 1-photon Fock states to logical 1 to restore the information. And also, you will know whether or not a single photon loss happened or not just by measuring the parity of the state without disclosing the C0 and C1 information. So basically, the procedure is just measure the parity. If there's no photon loss, you can actually know it's in the logical space. If there's a single photon loss, then you can perform the unitary to restore to the original information. So therefore, that's kind of the underlying idea of the Kitten Code. And now let's actually check, like using our error correction criteria to see like how this works. So now the error operators consists of identity and annihilation operator. And there are 2 possible error operators. So the EI dagger EJ, you can write it as a 2x2 matrix form. If I and J, EI, EJ both identity, it's identity. If EI identity EJ is A, it's an annihilation operator, or you can get A dagger or A dagger A. So those are the 4 possible like combinations for different EI, EJ. Now you can actually show this in terms of listing the table with phi k, phi l, which correspond to logical 0, logical 1, where again, logical 0 correspond to the symmetric superposition of 0 and 4-photon states, and logical 1 correspond to the Fock state with 2 photons. And you can compute the expectation values of this these 4 entries associated with the logical 0 or logical 1 from acting from left or right. And what you find is that when logical 0, logical 1, the off-diagonal part in this table, it basically vanishes. And in the diagonal part of this table, you actually get, this is basically the alpha ij. And you find that actually alpha ij is Hermitian, and also it has like, it's actually diagonal, which is a better situation so that there is no ambiguity of a mixing between different errors. So I'll put another way is actually whether or not you lose a photon, you will actually go into different parity space so that there is no off-diagonal terms in alpha ij. Okay, so this fulfills the error correction criteria. Okay, so that's kind of like a case that we can use error correction criteria to kind of verify that indeed the encoding for the Kitten Cad can correct the errors. And you can actually like, again, as I said earlier, intuitively, the average photon number is the same. So regardless what logical state, it's equal likely to lose photons. So there is no way for environment to infer what's going on. So in the second homework problem, actually, like I ask you to kind of do the same verification. And you may notice that actually the states I'm writing in the problem set is not calling this and that. I'm actually using as actually like some combinations of logical 0 and logical 1, call them to be logical 0 and 1s. But it actually doesn't matter because it's really, what matters is the projection to the code space. And you can choose different conventions for your logical 0 and 1. All right, so, and moreover, in the second homework problem, I also ask you to think about the generalization. Because so far, for this Kitten code, with up to 4 photons, you can correct a single photon loss. Then the natural question is, can we correct more photon loss? And the answer is yes, if you allow to use more photons to do the encoding. And there is actually a way to generalize this, is to call something called the binomial code. And binomial code is actually a design, which you may look into this detailed paper, is actually a design of single mode bosonic coding that can correct multiple photon loss errors. And the reason it's called a binomial code is actually the coefficient of different photon Fock states actually is the square root of a binomial. So it actually have a very interesting distribution of photon numbers, which follow the binomial distribution. But you choose a superposition in such a way that it allows you to correct multiple photon loss errors. And the previous case of 0, 2, and 4, this Kitten code, is actually correspond to a binomial code, which you have a binomial coefficient of associated with the 0 and 4, and the 4 and the 2 photon distributions. So that's actually something that in the second problem of the problem set, you will actually have a chance to explore another generalization of the Kitten code. And if you're really being very careful, thinking about the photon loss and back actions, you may find that actually the cross operator associated with photon loss is not just annihilation operator. It actually even if you don't have a photon loss, and that's also discussed in the supplementary of this paper, you'll find that if no photon loss, there is still a back action to the system. For example, if you have a coherent state, you don't have a photon loss, don't see any photon coming from the cavity. Actually, what happened is actually the coherent state amplitude will keep decreasing. That's because it's associated with the back action that you don't see any photon coming out. So it's more likely that there is a smaller number of photons in the system. And that will have some effect associated with the superposition of 0 plus 4 and 2. So 0 plus 4 will become 0 plus some coefficient in front of 4. And that coefficient will decrease the longer you observe. And similarly, for the 2 photon Fock state, that will also decrease. And then for that case, you actually need to make sure that you update and modify the states of your logical subspace. That overall, you can still balance these two and suppress error to the quadratic with kappa t. Okay, so in case you're interested, I would encourage you to look into this detailed paper discussing about this back action and how to correct these errors. Okay, so that's kind of like one type of bosonic code, which it's easier to think in terms of photon Fock basis. And we can come up with another bosonic code, which is called the Cad code. The Cad code is a code it's kind of have a connection to the classical coding called the phase shifted key. So kind of in our Wi-Fi and Bluetooth, we communicate classical signals by sending, in some sense, like coherent states, while the information is encoded in the phase of the coherent states. While for the Cad code, we can also use coherent states to form bases. For example, here we have 4 coherent states, which are like alpha, minus alpha, I alpha, and minus I alpha. So in principle, these 4 coherent states span a 4-dimensional space, which can encode 2 quantum bits. However, again, recall the principle of quantum error correction, we want to introduce redundancy to detect a single photon loss error. So we actually encode information in the odd photon subspace, which is associated with the symmetric superposition of alpha minus alpha and I alpha plus minus I alpha. So notice that these states, it's actually like, if you're familiar with quantum optics, you can expand these coherent states in the photon number basis, and you can verify they have an even number of photons. Or alternatively, if you think about the coherent states alpha plus minus alpha, you can rotate it by 180 degrees to give you the same states, that indicating it has an even number of parities, because 180-degree rotation is exactly the parity operator. Okay, so these two states have even number of photons. So therefore, if you have photon loss, that you will be able to detect them in terms of changing in parity. And you can keep having photon loss. And what happened is that after 4 photon loss, the state goes back to self. So all you need to do is actually monitoring the photon loss modulo 4, then you can recover the information. So now, instead of getting, let's maybe also use our quantum error correction criteria to test, okay, if these codes satisfy the condition. So now let's again write down the table associated with EI-EJ dagger, which consists of identity A or A dagger or product of A dagger A. And then let's plug into this table, which here horizontally listing logical 0, 1, vertical logical 0 and 1. And here we can get the 2x2 matrix correspond to this like expectation values of these different entries sandwiching by the corresponding logical 0 and 1 states. And what happened is that you'll find that these off-diagonal blocks guaranteed to be 0, while these diagonal blocks, they are approximately having the form that it's kind of like independent of the logical and 0. So this will define it to be alpha ij matrix. And notice that it's a diagonal form indicating that there's no mixing between different logical states, while the form of these alpha ij indicating that, well, there's a possibility of preserving the information. Okay, now, if we really did do the calculation, you will find that there is actually a subtle difference, that this term in here, it's not exactly alpha squared. There's a correction of e to the minus 2 alpha squared when it's depending on whether it's logical 0 or logical 1. And the off-diagonal terms also have some residual terms of order e to the minus 2 alpha squared. The reason is simple. It's because if you look into the phase space, even if there's no error, the states of alpha plus minus alpha and the superposition of I alpha plus minus I alpha, because the coherent states have the Gaussian distributions, they will always have some finite overlap between these different basis states. And that overlap is actually exponentially small with alpha, but it's not exactly 0. And that indicates that, say, even if you don't have photon loss errors, that there will still be some finite overlap between the different states. So that's actually related to like some concepts called approximated error correction. Is because what happened to this approximating being 0, this is only satisfied approximately. Okay, so in practice, actually, like it's good enough to just have approximated error correction, because even for the qubit case we talked about earlier, there could be an exponentially small chance that all the qubits get flipped, and you might mess up with error correction. But in practice, it's fine, because all we care is to correct a certain set of relevant errors and suppress them to high order. And similarly, for the bosonic case, even though it's approximated error correction, it's actually good enough for us to demonstrate the quantum error correction. Okay, so so here are some like illustration indicating the connection between the Cad code that we just discussed and the classical phase shifted keying that one may have. So there's actually another type of bosonic code, which we call the Gottesman-Kitaev-Preskill code, GKP code, named after the 3 inventors. So this code actually also has a connection to the classical coding, which is related to called the Quadrature amplitude modulation. So what is the Quadrature amplitude modulation code? It's a classical communication code that sends information encoding information in both amplitude and phase of a coherent state. Okay, you can write a coherent state as a complex number with the real and the imaginary components, which correspond to position and momentum. And then you can kind of discretize the position and momentum. You get a lattice, and you can, if you have 16 lattice sites, you can encode actually 4 classical bits. And this is kind of how the classical quadrature and amplitude modulation code works. And the GKP code, you can think it as a quantum version of the classical code. Instead of like using all these 16 lattice sites to encode 4 quantum bits, you actually just encode 2 quantum bits using these 16 lattice sites. And of course, there is some constraints about how the lattice spacing should be chosen. But if you satisfy those constraints, you can design the logical 0 and logical 1 as a superposition of these different coherent states with the appropriate coefficient associated with different coherent states. And that scheme actually allows you to encode like a quantum bits using oscillators. And you may notice that for coherent state, this GKP coding, it actually takes full advantage of the phase space, including in the vacuum regions, while for the Cad code, it only takes account the phase space, which is in a certain radius from the vacuum. So that actually gives us, it's actually related to later the performance comparison. The GKP code might be able to, because it uses a larger Hilbert space, it actually gives us better protection against photon loss errors. Yeah. So maybe let me just, since it's also related to like the understanding of how you correct errors, and there's a homework number 3, I give a question about like how can we evade the Heisenberg uncertainty principle? And that's also related to the GKP code. So here is actually one interesting observation related to the commutation relation. So as we all know, like we cannot simultaneously measure position and momentum of a one-dimensional system because position and momentum, they don't commute with each other. Okay, but you may notice the commutator here, I said h bar equal to 1 is actually a constant. And for such a constant commutator, you actually can use this BCH formula to show that if you perform a sequence of operations, which is e to the minus iap, indicating you do a displacement along the x direction, and then e to the minus ibx, indicating you do a displacement along the momentum direction. Then you displace back along the x and displace back in the momentum. And for this operation, you will find that actually it gives you an enclosed area in the phase space. And that operation will actually give you a geometric phase, which is e to the minus I phi. Okay, and phi is actually exactly equal to the area that's enclosed in the phase space. Now, that's actually indicating that generically, these 4 operators, or if you can move these 2 to the other side, which is basically the e to the iap and the e to the ibx, these 2 operators, generally they don't commute because e to the I phi is not equal to 1. However, for special cases when phi is equal to integer multiple of 2 pi, then you can actually make these 2 operators commute. For example, let's say phi is equal to a times b, while a and b both equal to square root of 4 pi, which is 2 times root 2 pi, then that actually encloses the area which is equal to 4 pi. And that actually allows us to design a GKP code. Okay, so before I move on to the GKP code, if these 2 operators commute, that indicating that you'll be able to simultaneously measure position and the momentum up to modulo some constant that determined by A and B. And that's related to the homework number 3. That indicating if you have a small change in displacement in position momentum, much less than kind of like a root pi, you actually may be simultaneously measure position momentum because you can design those operators associated with the position momentum modulo some like a choice of constants that allows you to simultaneously measure. But notice that that doesn't mean you can simultaneously measure position momentum because those operators still don't commute, but it is modulo of position momentum with some constant, those operators can be simultaneously measured. So that indicates if you have larger displacement or larger change in position momentum, you will not be able to resolve them. But if you only have a small change in position momentum, you can actually simultaneously measure them. And that's actually related to the design of the GKP code, because you can define, again, to our language of stabilizer code. This time the stabilizers are not product of polys. They're actually related to the displacement in the momentum direction and displacement in the position direction. Okay, displaced by 2 times root 2 pi. And those two operators, they commute with each other. Okay, so because they commute, you can come up with and also these operators, it's an exponential over Hermitian operator. So it's guaranteed to have an eigenvalue with a magnitude equal to 1. Or you can say this is a unitary operator, so the eigenvalue has to have a magnitude equal to 1. Okay, so now you can define a co-eigenstates of Sx and Xz with eigenvalue plus 1, and that defines actually a code space which is stabilized by the stabilizers Sx and Xz with eigenvalue plus 1. And one thing to notice is that different from polys, usually the stabilizers are Hermitian operators. Here the stabilizers are non-Hermitian because it's unitary, and however, it does not prevent us from measuring them, because if it's non-Hermitian operator, in principle, you can always design ways to measure the real part, imaginary part, and then reconstruct that value. Okay, so now here, the states we care is actually the co-eigenstates of these two stabilizer operators, which commute with each other with eigenvalue plus 1. So, moreover, we can also define logical operators, which define to be the square root of these stabilizers. Okay, and notice it's pretty easy to take a square root. You just remove a factor of 2 in the exponent. That corresponds to the logical z, corresponds to some displacement along the momentum direction, and logical x corresponds to kind of half of that displacement along the position direction. So here is just like an illustration of what corresponds to in terms of a displacement. So stabilizer Sx corresponds to displacing by 2 times root pi along the x direction. And Sz corresponds to displacing along the momentum direction by 2 times root pi. So the area enclosed by kind of making a loop around this is equal to 4 pi, which is definitely integer multiple of 2 pi's. So therefore, these two operators, Sx and Xz, they commute. Now we can also define the logical z as half of the displacement along the momentum direction, so that's logical z. And you can see that first the logical z and the Sz, you can also form kind of a loop, which will give you 0 area, which is also integer multiple 2 pi, so they commute. And the logical z and the Sx, so on one hand is 2 times root pi, the other hand is square root of pi, so the total enclosed area will be equal to 2 pi, which is also integer multiple 2 pi, so logical z and Sx, they'll commute. Similarly, you can verify Sz and the logical x, they also commute. So the only part which is non-trivial is actually logical x and logical z. So the enclosed area is only equal to pi, so that's indicating these two operators, the commutation relation is actually anti-commuting. Okay, so therefore you can show that ZL XL equal to e to the I phi XL ZL, and e to the I phi equal to pi, so it's equal to -1 times XL ZL. So this is consistent with the logical operation that you may want to perform by encoding a qubit into the system. Okay, so you can verify that all these commutation relations are satisfied. So just get some idea, what are these eigenstates look like? So just recall that, let's try to find the eigenstates associated with z, which is associated with displacing along the x direction by root pi. So the eigenstates with eigenvalue 0 would correspond to that all the x component. So it's displaced along the z direction by pi. So all the x components will have this integer multiple of root pi, while the logical one is all the integer multiple of root pi. So these two states will definitely be stabilized by actually the logical, the stabilizer Sx, because that's shifting everything by 2 times root pi. Okay, and if you apply logical x, shifting half a spacing, it goes from logical 0 to logical 1. So that's actually how these, like a blue lattice correspond to logical 0, red lattice correspond to logical 1. When you do like a shifting by root pi, you shift it by half a lattice. And so that's kind of like how we're going to function. This is along the projection of the x-axis, and this is a 2D we're going to function, how it looks like. So logical x and logical 0, logical 1. And you can get all these mappings by observing that, so let me highlighting kind of these sequence of red dots that will correspond to like you go from logical 0 to logical 1, you shift the lattice by root pi. Okay. However, for plus and minus, you actually shift it can be connected by the logical x operator. Okay, which connected by logical z operator, which connects the vertical displacement by square root of pi. And that's actually how you can see that these sequence of red dotted lines, how they are connected. Okay, so basically that shows that these are bosonic codes that can actually correcting, like how they actually correcting like a random displacement errors, and there's a mapping from the photon loss to random displacement by doing like a single mode, by like a phasing sensitive amplification. So that's why actually all these codes, the Cad code, Binomial code, and the GKP code with different lattices, they can all correct photon loss errors. So I think that will actually all I want to talk about with the bosonic coding, and that the key idea all comes from the full error correction criteria. But the key point is that now you can design, you have different ways to design the code to correct photon loss errors. Okay, so maybe it's a good time to pause and see if there are questions.
So far, there are no questions related to this section.
Okay, yeah, all right. So now I will maybe continue to maybe the last part related to error correction, and maybe we'll see like probably briefly also talk about the physical implementations and so on. So probably for the sake of time, I might not get into all the details given like the time constraint. So maybe so far we have talked about like how to design error correcting codes that can correct like qubit errors or photon loss errors for the bosonic case. But all the errors so far, we assume it's kind of more like memory errors, assuming all the error correction circuit can be perfect. Okay, but in practice, that we know that the error correction circuits may not be perfect. So actually, you may have like imperfect evolution, imperfect preparation of ancillary, and imperfect measurements. So all those would affect your performance of error correction, and you might introduce more errors than the errors you can correct. So the key idea is actually like to address this issue is to introduce something called fault tolerance. So the idea of the fault tolerant gate is that at the gate level, you may have all the P errors, but the hope is that after the gate operation into error correction, you can preserve the kind of like the information at the logical level, still maintaining the error to be of order P squared. Okay, so if we can do it, then that will actually maintain the suppression of error so that we can kind of, on one hand, keep preserving information at the logical level. On the other hand, we can also imagine doing concatenation to suppress error to higher and higher order by having more and more concatenation of errors. So for example, there are certain gates that can satisfy this property. And those gates are called transversal gates, which is, suppose you are doing a gate which is actually acting on individual encoding qubits on your block, individual physical qubits on your block, and not couple them. Then each of the qubits will have an error P. And that actually is consistent with the memory error. And we know that our error correction can correct memory error, suppress them to second order. Similarly, those gate errors acting on individual qubits can also be suppressed to second order. So therefore, that those individual, if we have a kind of transversal gates acting on individual qubits within each block, then you will be always have a guarantee to suppress error to second order. Okay, so now, moreover, for the quantum codes, like a CSS code, you can actually suppress, it's possible to implement not just a single logical qubit gate, but also two logical qubit gates, like a CNOT gate, and preserving the error so that each encoding block, that any operation error would only affect one of the qubits of the encoding block, so that the error kind of behaves just like a memory error, that you can suppress them to the high order. So as long as those errors are not correlated within the encoding block, then you will be able to suppress them to high order. So that's actually the requirement of fault-tolerant gate, is that you keep maintaining the property that the leading order error at the physical level, P, will be suppressed to P square at the logical level. Okay, there are different kind of designs to do the fault-tolerant circuits, but here, maybe for the sake of time, we're not going to get into them, but just to give the idea of how we can use concatenated coding and with these fault-tolerant gates to achieve to show the threshold and the suppressing error to high order. So now suppose we do have some encoded coding like that. Now here is actually the key idea of how we do fault tolerance, is that at the physical level, which we call the zeroth encoded level, the error scales as P, which P is a small parameter, but we want them to be even smaller at the logical level. So at the first level, then basically the errors are suppressed to P square. And there is actually an important prefactor C associated with the code and associated with the implementation of the circuits. But let's just denote it as a C, which is a given constant, which can be of order 10 to the 3 or 10 to the 4, depending on your design of the circuit. And you may look into Nielsen Chuang, page 479 for details. And this error is actually, this expression, you can also write it as C inverse of C times P square. And that's the error at the first encoded level. Now you can consider the error at the second encoded level. And here it's probably easy to add an intermediate step. Second encoded level is also C times epsilon 1 squared. And you can plug in the value of epsilon 1 here. You'll get this expression, which is C times CP square, which you can rewrite it as a C inverse times CP to the fourth power. Okay, then you can go to the rth order encoded level, and you'll find it's a C inverse CP to the power of 2 to the power R. So you may notice it's kind of like it's a kind of an exponential of the exponential. Okay, so basically it increased kind of doubly exponentially with respect to R, where R is the encoded level. So it's an exponential of the exponential, which indicating if we have a little bit increasing R, there will be a significant kind of suppression of the error, because here C dot P better be a number less than 1, so that you will get a reduction of the error when you have more and more encoding. Okay, so that leads to the kind of the question. First of all, one can immediately see that there is a threshold, that P needs to be less than a particular value called PC, which is equal to 1 over C. So here PC means P critical. So if P is less than this critical value, then P times C will be less than 1. So therefore you can keep raising, going to a higher level of encoding and suppressing error in this doubly exponential fashion. Okay, and moreover, you can consider that, so that's kind of this criteria that you need. If this is satisfied, then you will be able to keep suppressing errors. So if you want the error to be suppressed to a target value, let's call it targeted epsilon, then you want this epsilon r to be equal to the targeted epsilon. And that, because you have doubly exponential of the exponential, so we need to take a logarithm twice. So that leads to the level needed for the encoding is scales as a log of c times epsilon. And this number can actually can be very small. Just for example, if you have c times p to be 0.1, where c times epsilon, which say epsilon is about 10 to minus 30, then when you take a log of c epsilon with log base 0.1, this is a 30, and you take log base 2, that gives r equal to 5. So that indicates probably with 5-level coding, you can 5 concatenated level of coding, you can already suppress error to 10 to minus 30. So that can be a really, really small number. That's good enough for most of the computations that we're interested in. Moreover, the physical resources, and you can also go through the computation by checking the notes, it will only scale partly logarithmically, which is a polynomial of this log of the 1 over epsilon. So therefore, it can also be a very efficient circuit for coding. Yeah, so now I think that's probably like shows the idea that if you're below threshold, when CP is less than 1, your error correction, you can do quantum error correction to suppress errors to like a higher and higher order in this doubly exponential fashion. Okay, so I think that that's maybe all I want to talk about in terms of the fault tolerance method and the error correction threshold. And but there are some additional things that I would like to maybe also mention, and probably maybe you can spend time to read the notes and textbooks. So one question is actually how you can do a universal quantum gates. And it may be less trivial if you want to get like the full universal quantum computing. And so for example, for a particular code we call the 713 code, you actually can implement lots of gates, but all the gates we have is not universal. So from the control perspective, this is still not good enough. And from computation perspective, actually all the Clifford gates can be efficiently simulated. If circuits only have Clifford gates, you can design an efficient classical algorithm to simulate them. So what we need is something called a non-Clifford gates. So first, the definition of a Clifford gates are those gates that maps a Pauli into a Pauli operator. And for non-Clifford gates, it will not be such a map. And so here is actually like regarding a circuit design related to the theme of this spring school, is actually, you may notice that this is a circuit which is a combination of unitary evolution and measurement adaptive control. So psi is the unknown state you want to apply, you want to perform a quantum gate on. And you introduce an ancilla which consists of a superposition of 0 and 1, which has an extra controlled phase to e to the I pi over 4. And you do a C0 gate between controlled by the ancilla and acting on the system. And you measure the system in the computational basis and feed forward. If the measurement is 0, you do nothing. If measurement is 1, you perform additional SX gate, where S corresponds to a 90-degree rotation around the Z-axis. So once you did that, and here is actually the derivation, you will show that actually the whole evolution gives you this T gate, which is a non-Clifford gate combined with the other gates, you can achieve a universal quantum computing. Okay, so maybe I think that probably maybe for the sake of time, I would just leave it to the audience to look into more in the derivation here. But if you have questions, we can discuss more during the Q&A session as well. And so related to this measurement and also control, there's also important thing with in the error correction as well. Because here when we measure the syndrome, as I mentioned earlier, if you only have a single ancilla, measuring a syndrome which is a product of multiple Paulis, then that error in the ancilla might propagate to multiple qubit errors, which might be beyond the capability of error correction that we of the original coding. So the way to avoid it is called something called the fault tolerant measurement, is that you design something called the GHD states, which can be distilled and purified so that the error for the GHD state itself is already being suppressed. Then you can use the GHD state. Each of the GHD state, qubit in the physical qubit GHD state, will couple to a physical qubit in the encoding block. So any of the error happen to the physical qubits of the GHD state will only affect at most one physical qubit in the encoding block. Therefore, those errors can still be corrected with the error correction of the original encoding block. So therefore, you can still be immune to kind of like propagating errors from single operation error to multiple qubits. So that can still give you fault tolerant design. And that's crucial if you want to have a fully fault tolerant quantum circuits. Yeah, so I think that's probably related to the topic on the fault tolerance that I want to talk about. And I think, so if there are no additional question, I would move on to the last topic related to like the control and the measurements. So let me find, so this time I will go with the PowerPoint presentation and let me just set it up properly. All right. So I assume that people can see my presentation screen. If not, let me know. Okay. So
yes, no problem.
Now, okay, does that work, Chao? Yeah.
Yes, yes.
Okay, thank you. Yeah. So now I'm going to maybe try to like get to a bit more on this using the error correction and how we implement control and the measurements for real physical systems that want to do error correction. Okay, so here is just the motivation. Say actually we can use bosonic systems for different applications for communication, sensing, metrology, and simulations. But the challenge is photon loss error. And this part of the discussion will be mostly focusing on bosonic systems and how we actually using quantum error correction to correct errors in the bosonic system. And this is just to remind everyone, similar to qubits, we also, for quantum oscillators, we also use redundancy to correct errors, but different from qubits, which only have limited 2 levels, you have to introduce more qubits to introduce redundancy. Oscillators, we naturally have many higher levels that's sufficient for potentially give us redundancy for error correction. Moreover, the error models are different. For loss error, this has this a bosonic enhancement, but it only modifies the photon number by 1. So without going through all the error correction code again, which we covered early on, I would like to point out there are actually general 3 different approaches to control a quantum system. Okay, so maybe the first approach you'd probably be very familiar is actually to do unitary control. Okay, so you can just apply different unitary gates, and if you want, you can do measurement and use measurement feed forward control to take away entropy from the system or reset the system or do error correction. And there are also, you can combine unitary and dissipation. And I think some of the dissipations could be useful. And we'll talk about how to do that. And finally, more extreme case is you can only just use dissipation to achieve a full unitary quantum control. And this is, we'll talk about at the end of this discussion. So in order to understand the unitary control and maybe to appreciate more about how we actually perform error correction for bosonic system, so let me just briefly introduce what the system is. So it's a superconducting cavity qubit system. So you have a superconducting luminum, which you make 2 holes on it. Each of the hole will give you a bosonic cavity mode, which will be, because it's superconducting, so those cavity mode will be low loss with high quality. And the frequency of the cavity determined by geometry here is about a few gigahertz. And you may see a semi-transparent chip here, which is a sapphire chip hosting a Josephson junction, which is indicated here as a cross at the Josephson junction. And the second cavity is for readout, and for our purpose, let's not worry about it. So basically we have a bosonic mode storing information, and we have a transmon qubit for assisting the control. Notice different from Google IBM's experiment, here actually the superconducting qubit is really not used as a qubit, but used as a control unit to help us get the full control over the storage cavity. And the Hamiltonian is the following. So because the cavity and the qubit has very different frequencies, so they do not directly change excitation. They only have a dispersive coupling, which indicating depending on the state of the qubit, the cavity will have a frequency shift. Or interpreted differently is depending on the number of photons in the cavity, the qubit will have a different energy splitting between the ground and excited states. And that change of energy splitting is proportional to the photon number in the cavity. And the system is actually like really like in the quantum region, because the dispersive coupling of all the megahertz is about 1,000 times larger than the photon loss or the qubit decay. So here the photon I refer to microwave photon, which are about the gigahertz. So you really need to kind of cool the system down in the dilution refrigerator. However, the cavity can be really long-lived, about the tens of milliseconds, which is 2 orders of magnitude longer than qubits. So that also motivates people to think, okay, maybe we can store processing information in the cavity. Okay, and you can also, importantly, to read out the state of the qubit in a quantum non-demolition way, and then which very fast and with high fidelity. Moreover, for these experiments, typically you're operating in the like a few nanoseconds, like a typical time scales. So you need like a really fast FPGA adaptive control to condition on the measurement outcome to decide what to do in the next to control the system. So that's also available with FPGA control. So overall, that all these tools are ready. And now like we can look into, okay, the controllability of the system. So again, starting from this Hamiltonian, I'll put the cavity separately and put the qubit and the qubit cavity coupling as the second term. So these are the 2 terms. And then the cavity can have a drive. We can also drive the qubit. And it turns out that here is just the energy level diagram associated with the rotating frame of the cavity. So the cavity can have different photon numbers. The qubit can be in the ground or excited states. So now you have 2 sets of levels associated with the ground and excited states of the qubit with different cavity photon numbers. So when you drive the qubit, you don't change the cavity photon number. When you drive the cavity, you actually like only shuffle different cavity photon states and don't change the state of the qubit. And you see it's a fully connected graph. So that actually one can show you have a full universal control of the system. And related to Christina's talk, like earlier on, that you can actually using like optimum control schemes, like a Krotov algorithms, to come up with an efficient optimum pulse control to do a universal operation between the cavity and the qubit systems. So here you can get arbitrary unitaries for cavity and the qubits. Okay, so now how can we use these controls for our purpose in terms of like a quantum error correction? So here is a design that you can have a Cad code. Again, we talked earlier with the superposition of alpha minus alpha and I alpha minus plus minus I alpha. So these are even photons, and you can monitor in the parity to know whether or not there's a photon loss. Now the question is, how do we monitor the parity? Well, the answer is actually you can use a 2-level system to help you to perform a quantum non-demolition measurement of measuring the cavity. So here is the idea. So you prepare the transmon in a symmetric superposition of ground and excited states, and you let the transmon to dispersively couple to the cavity. So just remember that there will be depending on the number of photons, the transmon will have different phase accumulation, okay? And if you let the system evolve under this Hamiltonian for time pi over chi, then basically every photon will imprint an extra pi phase associated with the excited state of the transmon. So if you have even number of photons, then there will be integer multiple 2-pi phase for the excited state transmon, which effectively implements the identity operation for the transmon. And when you have odd number of photons, then there will be an odd integer multiple pi phase to the transmon, which effectively implementing a poly Z operation. So depending on the photon number parity, the transmon will go identity or poly Z operation. So if we start from a plus state, which is a symmetric combination of G and E, it will end up in plus or minus state, which are orthogonal states and only correlated with the parity of photon number. So that gives you a quantum non-demolition way to measure the parity of the system. And with such a measurement, we can repeatedly monitor the cavity, see if there's a photon loss or not. With the cat input, repeated parity monitoring, we know how we should interpret the encoded state as the output. And here is actually the experimental data with the horizontal axis being time and the vertical axis being the process fidelity, which is how good this entire storage is compared to the ideal operation, which should be identity operation on the logical encoded qubits. So in order to show that actually the experiment is actually error correction helps, it's actually important to compare with the best encodings you can have without error correction. And the best encoding you can have is actually in the presence of photon loss, is actually just using vacuum and the single photon state to encode the 1 qubit of information, because that has a minimum number of excitations and give you the minimum vulnerability to photon loss if you don't do error correction. And that has a lifetime about 300 microseconds. Then when you do this bosonic coding, you have more photon in the system. It actually, if you don't do error correction, it actually, the coherence time decays faster. But once you put in the error correction, you actually will find that actually a lifetime gets much longer. And that actually helps indicating that actually error correction can potentially, actually in this case, slightly improve the performance of the system. Okay, so now that actually corresponds to the case that we actually using the unitary control to unitary control and measurement feed forward to help us to do quantum error correction. Okay, however, this is not the only way. And here I want to point out that we can, in principle, introduce dissipation combined with the unitary to also help us to control the system. So one effect you might know is something called the quantum Zeno effect. The quantum Zeno effect, in a simple term, is basically saying if you kind of keep projecting the system to a particular quantum state, then it can inhibit all the dynamics that push the system away from that state. And that's actually the simplest case, which you only projecting the system to a single quantum state. But more generally, you can also project the system to a subspace associated, for example, with a logical code. Then in that way, you can actually not only stabilize the system, but also inhibit some of the slowly varying errors. So now let's actually look into one example of how to use the Zeno dynamics to help you to protect the encoded information. So here is just a simple schematic. You have a bosonic system in the cavity, and you have a transmon, and you can extract some of the information. Okay, and some of the errors we talked about are the photon loss error, and in practice there could also be dephasing errors. Maybe the cavity frequency gets slightly shifted, and maybe the shift, or maybe sometimes those stray microwave photons may pass through the cavity and shift its frequency. So how do we, and in terms of Lindbladian, those jump operators of photon and dephasing error is actually proportional to the photon number, and that's actually how the quantum jump operator and the Lindbladian equation will look like if you have these dephasing errors. So in order to correct the dephasing error, we actually can inspired by something kind of related to the engineer dissipation. So actually in the last homework problem, I talk about, about this driven damped harmonic oscillator. And I think in Ivan's homework problem, there's also one called a damped harmonic oscillator, which shows that if you have a coherent state, the system will undergo exponential decay back to the vacuum. The difference, and so for Ivan's that homework problem, you basically have just a photon jump operator associated with the photon loss, and that's the Lin-Blevin equation that you see here. Let me just get the pointer. Yeah, so basically you get this jump term, like a process associated with photon loss. Now the difference from that problem is now I actually add an extra drive to the bosonic system. So you actually drive the system with a resonant, like a microwave or optical fields, depending on your system. And once you have that drive, just like if you have a swing, you actually keep pushing it in the resonance, then actually it will reach to some like a steady state amplitude, because what happened is that the energy you put into the system compensates the dissipation. And now mathematically, you may find that this drive system with a Hamiltonian drive combined with dissipation is equivalent to a dissipation system, where the jump, the photon loss is actually modified to a jump A minus a constant, which is alpha infinity. So alpha infinity is kind of, you can think it as asymptotically, the system will be stabilized to a coherent state. And the energy you put in, the driving you put in, exactly cancels the dissipation for the system. And notice that for this driving and dissipation system, it actually drives it to a pure steady state. And it also suppresses the dephasing error. If you add the dephasing, push it around, it actually will keep pushing it back to the same original state of. And notice that usually we think dissipation introduces noise, but in this case, actually dissipation in some sense is a cooling, because it cooled to the particular pure state with no entropy. Okay, so now you'll find that for this case, you can stabilize it to a single state. And we can generalize it to stabilize it to a two-dimensional subspace by modifying to a d photon loss and a d photon drive, which kind of simultaneously take away or injecting d photon. When d equal to 2, it corresponds to squeezing. And that's kind of a schematic, say you can stabilize to the 2 points in the phase space, which actually in the Hilbert space, it corresponds to it's a two-dimensional subspace. You can put more drives in there. And I guess that's showing, maybe that's the animation-wise, you can see start from different states. It will actually like evolve into, let me start the animation again. Yeah, it will evolve depending on where you start from. It may end up in a different steady states. The reason is because the system has a two-dimensional steady state subspace. Therefore, the dynamics will evolve differently depending on what the initial state is. So if your initial state is in a logical state in the steady state subspace, then actually it will help you to protect against the dephasing noise. And so you may look into the in the references that actually you'll get the exponential suppression of dephasing error in the presence of this dissipation. So dissipation can actually help you to continuously correcting errors without this complication of measurement and feedback. So that's why actually like it's a very promising direction that potentially can simplify the hardware overhead and also all the classical feed-forward controls. Now, one natural question is how do we do logical operations? And here is actually the idea, which basically we use the xenodynamics to project the system to a steady state subspace. Then you can introduce a Hamiltonian perturbation, which is highlighted in blue, that actually may drive the system along a certain direction. But because the xenodynamics is very strong, it will, every time you deviate from the system, it will be projected back to the steady state subspace. Okay, so physically or mathematically, you can consider you just do the drive and deviate the system, and then you do the projection to the logical space. And because the projection happened like at a much higher rate, effectively you get an effective Hamiltonian evolution, which is a projected Hamiltonian projected to the logical space. And that turns out to be giving you a useful logical operator for computation. Okay, so if you really like to solve problems, this is actually something that you can, go through the exercise, verify that you can come up with different logical operators around X or Z or 2 qubit entangling gates by projecting to the desired logical space. Okay, so now, and there's actually a third situation that, oops, let me see. So there is a third situation that you can use all dissipation to control the system. And the idea is called the holonomic quantum control. So for the holonomic quantum control, it basically, the idea is that if a system going a closed loop, it actually may not necessarily evolve back to the initial state it starts from. Okay, so we probably remember this Fokker pendulum. If you kind of move around in a closed loop, it actually, the oscillation direction may be different from what you start from. And similarly, in the quantum domain, there is this Aharonov-Bohm effect, which is also kind of when you make a closed loop, actually there will be a non-trivial phase that to be enclosed, depending on the flux. And generally, you may have some, not just the overall phase, you may get some like a unitary evolution. And so that actually leads to the holonomic quantum computation. So here, that for the sake of time, I will not go into details, but just saying like, suppose I have engineered dissipation to stabilize the system to the two coherent states, alpha 1 and alpha 2. If I can make this alpha 1 to form a closed loop while keep alpha 2 unchanged, and as you will see from your homework problem number 3, when you make a closed loop, you actually accumulate a geometric phase, which is proportional to the area enclosed by the loop. So that will actually induce a logical operation, effectively shifting the fringes of the Cad state. Similarly, you can bring these two coherents together and then separate them. You can also perform the other logical operation, create a superposition of coherent states. So that actually turns out can give you universal control over the system, as well as you can even design coupling gates for it as well. So maybe just as maybe a take-home message for this, the control part is that you can use both unitary control as well as engineer dissipation, or combine unitary and engineer dissipation. One can achieve actually all kinds of operations that you may want for your quantum information processing. Yeah, so I think I'm already running out of time, and so I think that's probably where I will stop for today's lecture. Okay, so I think that maybe it's a time that maybe for people to work on the problems, and I think the links from that Richard sent to us, that we can use those links. Yeah, yeah. All right, and okay, so I'll probably see you in the other Zoom meeting. Yeah. Okay, all right. See you over there.